Deep in the early universe, 10.8 billion light-years away, lies a black hole so massive it defies everything we know about physics. TON 618 isn't just big, it's a cosmic titan, with a mass billions of times that of our Sun, swallowing matter and spewing energy across galaxies. Scientists are still baffled. How could something this huge form so quickly? In this video, we'll dive into the mystery of TON 618, exploring why it breaks the rules of black hole physics and what it tells us about the universe we thought we understood. What TON 618 actually is. TON 618 is not just another object in the night sky. It is a quasar unlike anything else ever recorded, a black hole so enormous it pushes the limits of everything we understand about the universe. At a distance of 10.8 billion light-years from Earth, the light that reaches us from TON 618 began its journey when the universe was barely a quarter of its current age. The light that hits our telescopes today has traveled across space for nearly 11 billion years, carrying with it the secrets of a cosmic monster that challenges the very rules of physics we rely on to understand black holes. The first hints of TON 618 came not from sophisticated space telescopes, but from an ambitious survey conducted on Earth. Astronomers in the 1950s at the Tonantzintla Observatory in Mexico were cataloging blue stars. Their goal was simple: identify objects that emitted unusually high amounts of light in the blue end of the spectrum. What they found was unusual, but at the time, no one could have guessed just how extraordinary it would turn out to be. The object was recorded in the Tonantzintla catalogue, given the designation TON 618, and for decades, it remained a curious entry in a list of stars. Its true nature was hidden, masked by the limitations of the instruments available at the time and by the immense distance separating us from it. Decades later, follow-up observations using radio telescopes revealed a startling truth. TON 618 was not a star. It was not even a simple object within a galaxy. It was a quasar, one of the brightest objects ever seen in the universe, powered by a supermassive black hole at its center. Quasars are already extraordinary. They are the engines of the cosmos, capable of outshining entire galaxies. They form when a supermassive black hole consumes surrounding gas, dust, and stars, producing massive amounts of energy in the process. The gas spirals inward toward the black hole, forming what scientists call an accretion disk. This disk reaches temperatures of millions of degrees, glowing so brightly that it can be seen across the universe, even when the black hole itself is invisible. But TON 618 was not just any quasar. Its luminosity, the total amount of energy it releases, is staggering. Observations suggest it shines with the intensity of hundreds of trillions of suns combined. The black hole at its heart is estimated to weigh around 66 billion times the mass of our Sun, a figure so enormous it is almost impossible to grasp. To put that into context, the supermassive black hole at the center of our Milky Way, Sagittarius A*, is roughly 4 million solar masses. TON 618 is more than 10,000 times heavier. The scale of TON 618 is almost incomprehensible, a true hypergiant in the realm of black holes. Quasars, including TON 618, are powered by the process of accretion. The gas and dust around the black hole are pulled in by its intense gravitational field. As the material spirals inward, friction and gravitational forces heat it up to extreme temperatures. The inner edge of the accretion disk can reach millions of degrees, emitting enormous amounts of energy in the form of light and X-rays. This process is so efficient that a small amount of material can release more energy than a star like the Sun does over billions of years. In the case of TON 618, this accretion process is happening on a scale that is unparalleled, making the quasar one of the brightest points in the observable universe. What makes TON 618 particularly remarkable is that it is so massive, so bright, and so far away, all at the same time. Most supermassive black holes known today are located in galaxies much closer to Earth, giving astronomers the ability to study their environments in detail. TON 618, on the other hand, exists at the edge of the observable universe. Its host galaxy is almost impossible to detect, drowned out by the extreme luminosity of the quasar itself. This makes it difficult to understand the conditions in which it formed, and the processes that allowed it to reach such an enormous mass in the early universe. TON 618 stands out not just because of its size, but because of the questions it raises about black hole formation. In the early universe, there simply should not have been enough time for a black hole to grow this large through normal processes. Black holes grow by consuming matter or merging with other black holes. Both processes take time, and the universe was still very young when TON 618 formed. Its sheer mass suggests that either it started as an unusually massive seed black hole, or it experienced a period of growth that exceeds the limits predicted by current models. Either way, TON 618 is a challenge to our understanding of cosmic evolution. When it was first studied in detail, astronomers relied on measurements of its light spectrum. The specific patterns of light emitted from the quasar, known as emission lines, reveal information about the speed of the gas in the accretion disk and the mass of the central black hole. By measuring these lines, scientists were able to calculate the extraordinary mass at the core of TON 618. This method, called reverberation mapping, allowed them to estimate not only the size of the black hole, but also the rate at which it was consuming material. The numbers were staggering, confirming that TON 618 was far larger and brighter than any known quasar at the time. TON 618 also challenges astronomers to think differently about the environments of early galaxies. If such a massive black hole existed when the universe was still young, the surrounding galaxy must have been rich in gas and matter to fuel its growth. Yet, even with the most powerful telescopes, the galaxy that hosts TON 618 remains almost invisible. The quasar itself outshines the galaxy, making it incredibly difficult to detect the stars and structures that might surround it. This has led scientists to speculate about the conditions that could have allowed such a black hole to grow so quickly. It may indicate that our understanding of early galaxy formation is incomplete, and that some of the most extreme objects in the universe may form under conditions we have yet to fully comprehend. Another reason TON 618 stands out is the scale of its accretion disk. The disk surrounding the black hole is enormous, stretching across a distance comparable to the orbit of planets in our own solar system. The inner regions spin at incredibly high speeds, approaching a significant fraction of the speed of light. This rapid rotation causes the disk to heat up even further, intensifying the brightness of the quasar. The outer edges of the disk are cooler, but they still radiate massive amounts of energy. This structure creates a system that is not only massive, but also highly dynamic, with enormous amounts of matter swirling around a central point of almost unimaginable gravity. The light from TON 618 also carries information about the early universe. Because the quasar is so distant, observing it is like looking back in time. When astronomers analyze the light, they can learn about the conditions in the universe billions of years ago. TON 618 provides a rare glimpse into the formation and growth of supermassive black holes at a time when the universe was still forming its first galaxies. The fact that it exists at all suggests that massive black holes could form much earlier than previously thought, forcing scientists to reconsider the timelines of cosmic evolution. In addition to its mass and brightness, TON 618 is also significant because it belongs to a class of objects known as hyper-luminous quasars. These are the brightest known quasars in the universe, capable of outshining entire galaxies. TON 618 is at the extreme end of this class, a record holder that pushes the limits of what astronomers believe is physically possible. Studying hyperluminous quasars like TON 618 helps scientists understand how matter behaves under extreme gravitational forces, how energy is released in the form of light and radiation, and how black holes influence the growth of galaxies over cosmic time. Despite its distance and brightness, TON 618 has become a key object in the study of black holes. It represents a case where theory meets observation and where existing models are tested against real data. The calculations required to estimate its mass, luminosity, and accretion rate are based on well-established principles of astrophysics, yet the numbers themselves are extraordinary. TON 618 forces scientists to confront the limits of our current understanding and to explore new possibilities for black hole growth, galaxy formation, and the evolution of the universe. TON 618 also demonstrates the importance of multi-wavelength astronomy. Observing the quasar requires instruments that can detect light across the spectrum, from visible light to ultraviolet and X-rays. Each wavelength provides a different piece of the puzzle, revealing details about the accretion disk, the speed of gas, the energy output, and the surrounding environment. By combining data from multiple telescopes and instruments, astronomers are able to build a more complete picture of TON 618 despite the enormous challenges posed by its distance and brightness. The discovery and study of TON 618 also highlight the collaborative nature of modern astronomy. Observations from ground-based observatories, radio telescopes, and space-based instruments all contribute to our understanding of this remarkable object. Teams of scientists analyze the data, compare results, and refine models to account for the extraordinary mass and luminosity of the quasar. Each piece of information helps to reveal the processes that drive one of the most extreme objects in the universe, offering a rare opportunity to study the limits of cosmic physics. TON 618 continues to be an object of fascination, not just because of its size, but because of the mystery it represents. Its existence raises fundamental questions about the early universe, the formation of black holes, and the behavior of matter under extreme gravitational forces. It is a reminder that the universe is full of surprises, and that even with the most advanced instruments and models, there are phenomena that challenge our understanding and force us to rethink what we know about the cosmos. The black hole at the center of TON 618 is a perfect example of nature operating at extremes. Its gravity is so intense that nothing, not even light, can escape from within its event horizon. The accretion disk, however, glows brighter than anything else in its vicinity, producing vast amounts of energy and revealing the presence of the hidden giant. This combination of invisibility and overwhelming brightness is what makes TON 618 a true cosmic paradox, a hyper-luminous object powered by an unfathomably massive black hole that defies simple explanations. The scale problem: why TON 618 should not exist. Black holes are among the strangest objects in the universe, regions of space where gravity is so strong that nothing can escape, not even light. They are formed through a process that we understand fairly well for most black holes. The first step is the collapse of massive stars. When a star exhausts its fuel, it can no longer support itself against gravity. Its core collapses, and if the mass is high enough, the result is a black hole. These stellar mass black holes are the seeds from which larger black holes can grow. Over time, through mergers with other black holes and the accumulation of gas, dust, and even stars, they can increase in size. But even with these mechanisms, there are limits to how quickly black holes can grow. We call one of these limits the Eddington limit, named after the astrophysicist Arthur Eddington. It describes the balance between the inward pull of gravity and the outward push of radiation generated by the hot gas falling into the black hole. If a black hole tries to pull in matter too fast, the radiation it produces pushes the gas away, slowing growth. This sets a ceiling on how fast black holes can increase in mass over time. For most black holes, this is not a problem because the growth process is already gradual. They merge with smaller black holes or slowly accrete gas from their surroundings, building up over millions or billions of years. TON 618 throws all of this logic out the window. It weighs around 66 billion times the mass of our Sun. That is more than 10,000 times heavier than Sagittarius, a star. the black hole at the center of our Milky Way. Even M87 star, the supermassive black hole recently imaged in the galaxy M87, is only about 6.5 billion solar masses. Ton 618 does not just break records, it shatters them. In the known universe, there is no black hole even remotely close to its size and brightness, especially not so early in cosmic history. The question is simple. How could something like Ton 618 grow so large in the time available? To answer that, we need to consider the usual paths for black hole growth. After a stellar collapse produces a small black hole, it can grow in three ways: by merging with other black holes, by accreting matter from surrounding gas and dust, or by consuming stars that wander too close. Mergers are powerful events. When two black holes collide, they combine their mass and release energy in the form of gravitational waves. Accretion is slower but steady. Gas and dust spiral toward the black hole, forming an accretion disk. Friction within the disk heats the gas to millions of degrees, producing intense radiation, but it also gradually feeds the black hole. Consuming stars is more chaotic and less efficient, but it can contribute additional mass. These mechanisms explain how supermassive black holes in the centers of galaxies can reach millions or billions of solar masses over billions of years. Ton 618 exceeds what these processes should allow. If a black hole grows at the maximum rate permitted by the Eddington limit, the math says it cannot reach tens of billions of solar masses in the first few billion years of the universe. Yet, Ton 618 existed when the universe was less than 3 billion years old. That leaves a profound discrepancy. Either Ton 618 grew faster than physics allows, or the starting seed was far more massive than anything we normally expect. Both options challenge our current understanding of how black holes form and evolve. Even the idea of a supermassive seed black hole is not enough to solve the puzzle. Scientists have theorized about direct collapse black holes, where a massive gas cloud in the early universe collapses without fragmenting into stars, forming a black hole with hundreds of thousands or even a few million solar masses. But even this method falls short. To reach 66 billion solar masses, a black hole would still need to grow at rates beyond the limits imposed by the Eddington ceiling. The mass of Ton 618 is too great for the time available, and no observed environment in the early universe seems capable of providing enough material to feed it fast enough. The Eddington limit sets a maximum accretion rate, meaning the amount of matter a black hole can consume before radiation pushes back against the inflow. For a black hole the size of Ton 618, the rate required to reach its mass in less than 3 billion years is many times higher than the Eddington limit. This suggests that either physics behaves differently under extreme conditions, or there is a mechanism we have not yet discovered. Every calculation, every model of black hole growth struggles to account for its size. Ton 618 exists at a scale that tests the limits of astrophysics itself. Comparisons make the scale easier to grasp. Sagittarius. A star has a mass of about 4 million solar masses, making it tiny next to Ton 618. M87 star, one of the largest black holes observed in the local universe, is still only a fraction of Ton 618's mass. Even quasars that shine brightly and consume matter rapidly are dwarfed in comparison. Ton 618 is in a league of its own, a Titan black hole. A term scientists use not because it is official, but because it is the only word big enough to describe it. There is no classification that can properly capture its enormity. It sits at the extreme edge of the possible, a true cosmic outlier that stretches the rules of what we know. The timeline problem adds another layer of complexity. The universe was only a fraction of its current age when the light from Ton 618 began its journey toward Earth. That means the black hole had to reach its mass in a relatively short window of cosmic history. Black holes grow gradually and even the fastest theoretical growth models require millions of years to double in mass. TUN 618, however, achieved a mass so vast that standard models of black hole growth cannot account for it. This timeline problem is one of the reasons why it continues to fascinate astronomers. It is not simply large, it is an anomaly that demands new thinking about the early universe. TUN 618 also challenges our understanding of mass accretion rates. To sustain such rapid growth, the black hole must have been surrounded by an enormous supply of matter. Gas, dust, and stars would need to funnel continuously into the accretion disk at rates far exceeding what is typical for known quasars. Maintaining such a supply over millions of years without disrupting the surrounding galaxy is difficult to explain. It requires an environment of extreme density and abundance, conditions that we rarely observe. The problem is not just feeding the black hole. It is feeding it consistently, efficiently, and at the scale required to reach tens of billions of solar masses. This is why TUN 618 stands out so sharply from other quasars. Most quasars, even the brightest ones, are massive by normal standards, but still fall within the expected range of growth for black holes in the early universe. TUN 618, in contrast, is extreme in every sense. Its mass, luminosity, and age combine to make it one of the most challenging objects to explain. Every detail of its existence pushes the limits of our models. It is the extreme case, the boundary object that tests the edges of what we consider possible. When scientists refer to TUN 618 as a Titan black hole, it is more than just a nickname. It signals that this object is not simply large, but massive, far beyond the scale of conventional supermassive black holes. It occupies a category that is currently undefined in astrophysics. No official classification exists for objects of this size, yet TUN 618 demands one. It is the type of object that forces astronomers to think beyond standard frameworks, to consider new possibilities for black hole formation, and to question assumptions about the early universe. TUN 618 size also has implications for the galaxies that host it. Black holes and galaxies evolve together. The mass of a black hole is generally correlated with the mass of the central bulge of its galaxy. If TUN 618 is 66 billion solar masses, then its host galaxy must have been extraordinarily massive, capable of supplying the black hole with enough gas and stars to fuel its growth. Yet, even with modern telescopes, the host galaxy remains difficult to detect, overwhelmed by the quasar's immense brightness. This adds another layer to the mystery. How could a black hole grow so large without leaving clear evidence of the galaxy around it? The scale problem of TUN 618 extends to its accretion disk and luminosity. A black hole of this size produces radiation at incredible levels. Its accretion disk spans distances comparable to the orbits of planets in a solar system, with inner regions spinning at speeds approaching the speed of light. The energy output is immense, outshining hundreds of billions of stars combined. Maintaining such a disk and such luminosity without destroying the surrounding material or violating physical limits is a puzzle that current astrophysical models cannot fully solve. The extreme mass of TUN 618 also highlights gaps in our understanding of black hole seeds. If it began as a stellar mass black hole, there simply would not have been enough time for it to grow to tens of billions of solar masses in the early universe. If it began as a direct collapse black hole, the initial mass would have been large, but still insufficient to reach the observed mass without sustained accretion at rates higher than theoretical limits. TUN 618 forces the question: are there unknown processes in the early universe that allow black holes to grow faster than expected? Or are our models of mass accretion and growth incomplete? The comparisons to other black holes make the scale of TUN 618 even more evident. Sagittarius, a star, our Milky Way's central black hole, is tiny by comparison. M87 star, which dominates its galaxy, is immense, but still only a fraction of TUN 618. Other quasars, even some of the brightest known, do not approach this scale. TUN 618 is so far beyond the ordinary that it has earned the label Titan black hole, an informal classification that conveys the sheer size, energy, and anomaly of the object. What TUN 618 looks like up close. TUN 618 is a quasar so extreme that approaching it, even conceptually, challenges everything about scale and energy in the universe. Its most striking feature is the accretion disk that surrounds the black hole, a disk of gas, dust, and plasma, heated to millions of degrees Kelvin. The temperatures in this disk are so high that the material glows brighter than entire galaxies. The disk is a continuous spiral of matter, drawn inward by the black hole's immense gravity. Every particle in this disk moves at incredible speeds, some approaching a significant fraction of the speed of light. Friction and gravitational forces convert kinetic energy into heat, and the heat turns into radiation that blazes across space in all directions. The light coming from the disk is so powerful that it can be detected from billions of light years away, providing the first signs of TUN 618's presence. The structure of the accretion disk is not uniform. The inner regions, closest to the black hole, are the hottest and brightest. Here, gas particles collide violently, producing high-energy X-rays that radiate outward. Moving outward, the disk cools gradually, but even the outer edges remain incredibly luminous. These outer regions emit visible and ultraviolet light, contributing to the quasar's extraordinary brightness. For comparison, if TUN 618 were placed at the center of our Milky Way, its disk alone would outshine all the stars in the galaxy combined. This makes the quasar not just a bright point in space, but a beacon visible across enormous cosmic distances. Relativistic jets are another signature feature of TUN 618. These are narrow streams of charged particles ejected at nearly the speed of light, perpendicular to the plane of the accretion disk. Jets form when magnetic fields in the disk become twisted and compressed. The energy from the spinning black hole and the accreting material channels into these jets, sending particles shooting out across intergalactic space. TUN 618's jets are likely hundreds of thousands of light-years long, carrying energy far beyond the galaxy it resides in. While the black hole itself is invisible, the jets are luminous across the electromagnetic spectrum, from radio waves to X-rays, tracing the influence of the black hole far into the surrounding cosmos. Time behaves differently near TUN 618. The gravity of a black hole curves space and slows time relative to observers farther away. This effect, predicted by Einstein's theory of general relativity, is called time dilation. If a spaceship were to approach the event horizon of TUN 618, time for those aboard the ship would pass more slowly compared to people observing from a safe distance. Even light escaping from the inner edges of the accretion disk experiences shifts in frequency, appearing stretched or redshifted to distant observers. These effects make the quasar a natural laboratory for studying the extreme physics of gravity and motion. The event horizon itself marks the boundary of the black hole, the point beyond which nothing can escape. For TUN 618, this boundary is unimaginably vast. The Schwarzschild radius, the distance from the black hole's center to its event horizon, is estimated to be about 195 billion kilometers. To put this in perspective, that distance is roughly 1,300 astronomical units, with 1 AU representing the distance from Earth to the Sun. The orbit of Neptune, the outermost planet in our solar system, is just 30 AU from the Sun. TUN 618's event horizon spans distances over 40 times larger than the entire orbit of Neptune, encompassing a volume far beyond anything in our own solar system. As you move closer to the black hole, the gravitational pull becomes extreme. The inner regions of the accretion disk are subject to tidal forces that stretch and compress matter. Gas spirals inward in tightly wound paths, forming intricate patterns of motion. Magnetic fields become tangled and twisted by the disk's rotation, helping to channel energy into the relativistic jets. Radiation pressure is so intense that it can push gas outward even as gravity pulls it inward. The balance of forces in this environment is delicate, yet stable enough to sustain the quasar's extraordinary luminosity over millions of years. The scale of Ton 618's accretion disk is mind-boggling. While the event horizon is 195 billion kilometers across, the disk extends far beyond that. Gas and dust at the outer edges orbit at slower speeds, but still generate significant heat and light. The disk structure resembles a flattened, spinning spiral, with layers of material interacting through friction, magnetic forces, and gravitational torques. The energy radiated by the disk is what makes Ton 618 detectable from 10.8 billion light-years away. Even as photons travel across the universe, the brightness remains intense enough to mark it as one of the most luminous objects in the cosmos. Jets form along the black hole's axis of rotation, shooting away from the disk at nearly the speed of light. These jets are composed of electrons, protons, and atomic nuclei, confined by magnetic fields that twist and coil along the axis. The material within the jets is accelerated to relativistic speeds, causing emissions across multiple wavelengths. Ton 618's jets extend far beyond its host galaxy, transferring energy into intergalactic space and affecting the surrounding cosmic environment. Observations of the quasar's jets provide insight into the mechanics of black hole accretion and energy release, allowing scientists to study processes that cannot be reproduced in laboratories on Earth. Time dilation becomes extreme at the edge of Ton 618. Near the event horizon, seconds for a distant observer may correspond to fractions of a second for material orbiting close to the black hole. This effect stretches the duration of events as seen from far away, meaning the inner accretion disk appears to move slower to an external observer. Light emitted from these regions is gravitationally redshifted, shifting towards longer wavelengths. This combination of gravitational time dilation and redshift changes the way Ton 618 appears to observers, making it a unique probe of the laws of physics under extreme conditions. The inner edge of the accretion disk lies just outside the event horizon. Here, matter orbits at relativistic speeds, colliding and heating to millions of degrees Kelvin. These collisions produce high-energy radiation, which radiates outward and can be detected across billions of light-years. Moving outward, the disk gradually cools, emitting light at longer wavelengths. The interplay of gravity, velocity, and magnetic forces in this region creates a dynamic, energetic environment unlike anything experienced in the solar system or even within other galaxies. If you could approach Ton 618 from light-years away, it would dominate the sky. The quasar's light outshines nearby stars, dwarfing the combined luminosity of its host galaxy. Even at distances of tens of thousands of light-years, the quasar would appear as a point of intense brightness, sending streams of radiation across space. As you move closer, the disk would spread across a large portion of your view, its inner regions flickering with X-rays and ultraviolet light. The jets would extend perpendicular to the disk, bright streams of matter stretching into the darkness. The scale of Ton 618 is such that even a journey of several million kilometers toward it would not diminish its overwhelming presence. Ton 618's accretion disk also creates unique observational effects. Light from the far side of the disk curves around the black hole due to gravitational lensing, allowing observers to see regions that would otherwise be hidden. The rotation of the disk produces Doppler shifts in the emitted light, with parts moving toward the observer appearing bluer and parts moving away appearing redder. These effects allow astronomers to measure the speed of the disk and estimate the mass of the black hole, confirming its extreme size and power. Every photon detected carries information about the physics at play in this extraordinary environment. The distance to the event horizon, the size of the accretion disk, and the length of the jets all emphasize the sheer scale of Ton 618. Its event horizon alone is thousands of times larger than the orbit of Pluto, and the accretion disk stretches much farther. The jets extend across distances comparable to entire galaxies. Even from great distances, the quasar is visible because of the intensity of its light, allowing astronomers to study its structure and behavior despite being billions of light years away. Relativistic jets from TUN 618 also illustrate how energy is transferred over enormous scales. Magnetic fields guide the jets, keeping them collimated as they travel vast distances. Material in the jets moves at speeds close to light, carrying both matter and energy far from the black hole. These jets interact with surrounding gas and intergalactic matter, producing shockwaves and radio emissions detectable across the universe. By studying these jets, scientists can infer the properties of the black hole's rotation, the strength of magnetic fields, and the dynamics of the accretion process. As you conceptually move closer to TUN 618, gravitational forces intensify rapidly. Tidal effects stretch and compress matter in the inner disk, while relativistic speeds and magnetic fields generate powerful emissions. The combination of heat, motion, and radiation produces a luminous, turbulent environment. Despite this chaos, the accretion disk remains coherent, funneling matter inward while channeling energy into the jets. This balance is a defining feature of quasars, and is particularly extreme for TUN 618, where the mass and luminosity are unprecedented. TUN 618 provides an example of how black holes influence their surroundings on multiple scales. The inner accretion disk produces intense radiation that affects nearby matter, while the jets deliver energy far beyond the host galaxy. The gravitational pull shapes the orbits of gas clouds and stars in the central region. Light from the quasar carries information about these processes, allowing astronomers to reconstruct the structure and dynamics of this massive system. Observations reveal the inner workings of an object at the extreme limits of mass, energy, and gravity. TUN 618's accretion disk also demonstrates the relationship between mass and luminosity in black holes. The extreme mass of the black hole generates gravitational forces that pull matter inward at high speeds, creating the friction and heating necessary to produce incredible luminosity. The energy output is proportional to the mass and spin of the black hole, making TUN 618 one of the brightest objects known. The accretion disk acts as both a feeding structure and an energy source, converting gravitational potential energy into radiation visible across the universe. The quasar's structure can be understood as layers of matter in orbit, with inner layers hotter and faster, and outer layers cooler and slower. Magnetic fields thread through the disk, twisting and storing energy that powers the relativistic jets. Radiation escapes from the disk, providing the light that allows astronomers to measure the black hole's properties. Gravitational forces shape the motion of the material, creating spiral flows and turbulent eddies. Each component interacts with the others, forming a complex, energetic system that is both massive and highly dynamic. Time dilation near TUN 618 is a constant factor in its observational properties. Photons emitted near the event horizon take longer to reach distant observers due to the curvature of space-time. The disk appears to move more slowly, and the frequency of light shifts due to gravitational redshift. These effects allow scientists to measure the strength of the black hole's gravity and to study the behavior of matter under extreme relativistic conditions. The combination of mass, rotation, and gravity makes TUN 618 a laboratory for high-energy physics on a scale far beyond any human experiment. The accretion disk and jets together define the visual identity of TUN 618. The disk glows with intense light, the jets extend far into space, and the event horizon marks the boundary of the black hole's influence. Observing the quasar from light years away, the brightness dominates the surrounding region. The jets can be detected at radio wavelengths, tracing energy flowing across intergalactic distances. Light from the inner disk carries information about motion, temperature, and magnetic fields. Every measurement provides insight into the mechanics of an object that is extreme even among quasars. Ton 618 size, luminosity, and energy output are unprecedented. The event horizon is hundreds of billions of kilometers across. The accretion disk is millions of degrees hot. Relativistic jets carry energy over distances longer than entire galaxies. Time behaves differently near the black hole, stretching and shifting the light that reaches us. Every detail of the quasar's structure pushes the limits of what is observable and measurable, making it one of the most extreme environments known. Even from light years away, TWON 618 dominates the sky. Its accretion disk and jets mark it as a source of enormous energy. Photons traveling across billions of light years carry information about mass, rotation, and luminosity. Gravitational forces shape the disk, accelerate the jets, and stretch time. Magnetic fields twist and channel energy. Every aspect of Ton 618's appearance reflects the extreme conditions near one of the largest black holes ever discovered. Why Ton 618 breaks all the rules. Ton 618 is a black hole that doesn't play by the usual rules. Every black hole in the universe follows certain physical limits, but Ton 618 exists outside all of them. Understanding why it's a problem requires looking at the numbers and the physics that govern black holes. One of the first challenges scientists face is called the Eddington limit. The Eddington limit defines how fast a black hole can grow by consuming matter. As gas and dust fall into a black hole, they heat up and emit energy. The hotter the material, the more radiation it produces. This radiation pushes back on the infalling matter, creating a natural cap on how quickly the black hole can gain mass. Go beyond this limit, and the black hole literally blows away the material it's trying to swallow. Most black holes in the universe stick to this limit. Even supermassive black holes in nearby galaxies follow it. But Ton 618 is estimated to be 66 billion times the mass of our Sun. To reach that size, it would have needed to consume matter far faster than the Eddington limit allows. That means at some point, it should have blasted most of its food away with radiation pressure, slowing growth. Yet here it is, bigger than anything astronomers expected possible. How did it manage to grow so fast without destroying the very material that fueled it? Scientists call this the Eddington limit problem, and Ton 618 is the ultimate example of it. The timeline of the universe adds another layer of difficulty. Ton 618 existed when the universe was only about 3 billion years old. That's young on a cosmic scale. Black holes grow gradually. They start as small seeds, either from the collapse of massive stars or from hypothetical direct collapse mechanisms, and build up mass over millions or billions of years. The universe simply wasn't old enough for a black hole to reach 66 billion solar masses using classical growth processes. Every calculation, every simulation hits a wall. Classical models of black hole formation cannot account for Ton 618's mass in the early universe. Accretion efficiency makes the problem even worse. Not all the matter that falls toward a black hole actually adds to its mass. A significant portion of it is converted into energy and radiated away. For every kilogram of gas that spirals in, a fraction is lost as radiation. This is called the accretion efficiency. Typical efficiencies range from 10 to 40% depending on how the black hole spins. For Ton 618 to reach 66 billion solar masses, it would have needed to accrete far more material than seems plausible, given the time available. The numbers just don't add up. This brings us to the black hole seed problem. Black holes begin as seeds, and their starting size affects how quickly they can grow. Stellar seeds form from the collapse of massive stars, with initial masses of a few tens of solar masses. Even if a stellar seed accretes at the maximum rate allowed by the Eddington limit, it would take much longer than 3 billion years to reach 66 billion solar masses. Ton 618 breaks the rules here too. Its starting seed cannot have been a typical stellar mass black hole. Direct collapse seeds were proposed to address this problem. In this scenario, massive clouds of gas in the early universe collapsed directly into black holes without forming stars first. These seeds could reach tens or hundreds of thousands of solar masses from the start. That's enormous compared to stellar seeds. But even with direct collapse seeds, calculations show that growth to tens of billions of solar masses in under 3 billion years is still extremely difficult. TON 618 requires an explanation beyond classical models. Classical black hole formation models fail spectacularly in this case. They assume that black holes grow steadily by consuming matter while obeying physical limits like the Eddington cap. They assume realistic conditions in early galaxies with a finite supply of gas and dust. They account for accretion efficiency, radiative losses, and mergers with other black holes. Yet TON 618 is outside all of these bounds. It reaches 66 billion solar masses, shining with luminosity that outshines entire galaxies, all while existing in a universe that was still in its early stages of evolution. TON 618 is so bright that it hides the galaxy it belongs to. Normally, a black hole of any size sits at the center of a galaxy, surrounded by billions of stars. The galaxy and the black hole evolved together. The mass of the black hole generally scales with the mass of the galaxy's central bulge. With a black hole as massive as TON 618, astronomers would expect an enormous galaxy surrounding it, full of stars, gas, and dust. But that galaxy is almost invisible. TON 618 is so luminous that its light drowns out the host galaxy entirely. Scientists cannot clearly see the stars or structure around it. This is a major problem for astrophysics. Black holes do not exist in isolation. Every black hole with measured mass lives in a galaxy, and there is a relationship between the two. TON 618's host galaxy should be extraordinary, yet it is not visible. This makes it impossible to test theories of galaxy formation and evolution for this quasar. Without a visible galaxy, astronomers cannot confirm whether the environment matches the predictions required to feed a black hole of this size. The missing host galaxy also challenges the concept of coevolution. Black holes and galaxies typically grow together. Gas that feeds the black hole also fuels star formation in the surrounding galaxy. Massive black holes influence the distribution of matter, shaping the evolution of their host. TON 618 breaks this relationship. Its black hole is enormous, yet the galaxy appears faint or absent. If the galaxy is small, how could it have provided enough material to grow the black hole to 66 billion solar masses? If the galaxy is large but hidden, what conditions allowed it to feed the black hole without revealing itself? Either answer creates tension with standard models. The Eddington limit, the early universe timeline, accretion efficiency, black hole seeds, and the missing host galaxy all combine to form a web of paradoxes. TON 618 exists where classical physics says it should not. Every model that predicts growth over cosmic time fails to produce a black hole of this mass so early in the universe. The accretion limit suggests it cannot eat fast enough. Efficiency losses indicate it cannot convert enough mass, and seed size indicates it cannot start big enough. On top of that, the galaxy that should be visible as the feeding ground is almost completely hidden. This combination of problems is why TON 618 continues to puzzle scientists. It is an extreme outlier in every measurable way. Its mass is off the charts. Its brightness outshines galaxies, and its environment does not match expectations. Classical models of black hole growth, designed to explain other quasars and supermassive black holes, simply do not apply. TON 618 exists beyond the edge of what current astrophysics can describe. Scientists have tried to reconcile these issues in multiple ways. Some suggest periods of Super-Eddington accretion, where the black hole consumes matter faster than the theoretical limit. This could allow faster growth, but is difficult to sustain over billions of years. Others propose that mergers with other black holes contributed a large fraction of the mass. While this is possible, it would require a highly unlikely series of events in the early universe. Direct collapse seeds help, but not enough to solve the timeline problem entirely. TON 618 remains a challenge because every proposed solution stretches known physics to its extreme. The problem with TON 618 is not just the numbers, it's what it tells us about the early universe. If a black hole of this mass can form so quickly, then our understanding of cosmic evolution is incomplete. We may be missing mechanisms for rapid black hole growth, or the distribution of matter in early galaxies may be very different from what we assume. The quasar forces astronomers to rethink the timeline for structure formation in the universe, highlighting gaps in our models and assumptions. TON 618 is a cosmic paradox. Its luminosity hides the galaxy it should inhabit, its mass defies growth limits, and its existence challenges timelines. The Eddington limit says it shouldn't have grown this fast. Stellar seeds say it couldn't have started big enough. Direct collapse seeds help, but don't solve the problem. Accretion efficiency ensures that much of the infalling matter becomes radiation rather than mass. Every factor makes its growth seemingly impossible, yet TON 618 exists. The missing host galaxy is particularly troubling. In most quasars, astronomers can study the stars, gas, and dust that surround the black hole. These observations test models of coevolution and feed predictions for black hole growth. With TON 618, the galaxy is invisible, drowned out by the quasar's brightness. That makes it impossible to confirm whether the environment matches theoretical requirements. Without a visible galaxy, a central tenet of black hole science, that massive black holes sit in massive galaxies, is challenged. TON 618's brightness also limits what we can learn. Its light is so intense that it overshadows everything around it. Even powerful telescopes cannot easily separate the quasar's emission from any underlying stars. This makes the black hole a mystery, not only in mass and growth, but also in its context. The environment that should explain its formation is hidden, leaving scientists with only indirect evidence and forcing reliance on models that are already pushed to their limits. Every classical model fails to explain TON 618. Growth rates, timelines, seed masses, accretion efficiency, and host galaxy visibility all combine into a single unsolvable puzzle. The quasar exists at the extreme edge of physical possibility. It is not just an outlier, it is a challenge to our understanding of black holes, galaxies, and the early universe. The numbers, the physics, and the observations collide in a way that leaves no easy answers. TON 618 forces scientists to confront the limits of current astrophysics. Its size, age, and brightness cannot be reconciled with known growth mechanisms. Stellar seeds are too small, direct collapse seeds too modest, the Eddington limit too restrictive, and the host galaxy too faint. The quasar operates at a scale that classical models cannot reach. Every attempt to explain it highlights gaps in our understanding, showing that the universe still holds surprises far beyond what we can imagine. Even considering mergers, Super-Eddington accretion, and hypothetical conditions in the early universe, the black hole's growth remains a problem. Classical equations predict limits on mass, luminosity, and accretion. TON 618 exceeds all of them. It shines so brightly that it blots out its galaxy, yet it weighs more than 66 billion suns. The combination of extreme mass, early age, and missing galactic context makes it an object without precedent. This is why TON 618 is often called a Titan black hole. It doesn't just break records, it defies expectations. The scientific theories and why they fall short. TON 618 is not just a massive black hole. It is a cosmic anomaly that pushes the boundaries of everything astronomers thought they understood about black hole growth. Scientists have tried to explain its size with multiple theories, each rooted in established physics, yet each theory falls short when applied to the extreme mass of this quasar. One of the first ideas scientists considered is Super-Eddington accretion. The Eddington limit defines the maximum rate at which a black hole can consume matter before the radiation generated by infalling material pushes the rest of the gas away. It is a kind of cosmic speed limit for black hole growth. Standard accretion, limited by this threshold, cannot explain how TON 618 reached tens of billions of solar masses in the early universe. Super-Eddington accretion is a theoretical process in which a black hole bypasses this limit, swallowing matter faster than classical physics suggests. In this scenario, the inward pull of gravity overcomes the outward radiation pressure, allowing the black hole to grow more quickly than usual. The idea of Super-Eddington accretion is appealing because it provides a potential path for rapid growth. In simulations, a black hole consuming gas at several times the Eddington limit can gain mass at extraordinary rates. The inner regions of the accretion disk become thick and turbulent, and some of the radiation escapes in funnels perpendicular to the disk, allowing the black hole to keep eating. This process could, in theory, allow a black hole to grow several times faster than standard models predict. However, when applied to TUN 618, Super-Eddington accretion still falls short. Even under ideal conditions, sustaining this rate for billions of years is extremely difficult. The early universe provides limits on the amount of gas available, the stability of accretion flows, and the ability of the black hole to avoid blowing away its own fuel. In practical terms, the mathematics shows that while Super-Eddington accretion can boost growth, it cannot account for a black hole reaching 66 billion solar masses in less than 3 billion years. The problem is not just the speed. It is maintaining the speed for long enough to reach TUN 618's mass. Another scenario explored is direct collapse black holes. In the early universe, some massive clouds of primordial gas could collapse directly into black holes without fragmenting into stars. These clouds could contain between 100,000 and 1 million solar masses of material, far more massive than a typical stellar seed. A direct collapse black hole starts life with a significant head start, bypassing the slow growth from a stellar collapse. This model is particularly useful for explaining supermassive black holes at high redshift, where the universe is young and time is limited. Starting with a seed of hundreds of thousands of solar masses reduces the growth time required to reach billions of solar masses. For many quasars, this could offer a viable path to extreme mass in a relatively short cosmic window. For TUN 618, however, even a direct collapse seed is insufficient. A starting mass of 1 million solar masses is still far too small to reach 66 billion solar masses in the universe's early years. Calculations show that the black hole would need to accrete at or above Super-Eddington rates continuously, which, as already explained, is extremely difficult to sustain. The numbers simply do not add up. Direct collapse black holes reduce the problem, but do not eliminate it. TUN 618 remains outside the range predicted by classical growth scenarios. A third possibility involves runaway mergers in dense star clusters. In this scenario, a dense cluster of stars at the center of a galaxy could produce repeated collisions, forming larger and larger black holes. As stars collide and collapse, intermediate mass black holes merge, creating a chain reaction that increases mass quickly. In principle, this could produce a massive black hole faster than standard accretion allows. Runaway mergers rely on extreme densities and high rates of collisions. While simulations suggest this can happen in the cores of very dense clusters, the speed required to reach TUN 618's mass is beyond what models predict. Collisions produce heat, radiation, and gravitational interactions that disrupt the cluster over time. Maintaining the conditions necessary for continuous mergers long enough to form a 66 billion solar mass black hole is highly unlikely. Runaway mergers may contribute to growth in some cases, but for TUN 618, they cannot account for the full mass. A fourth scenario is galaxy merger cascades. Galaxies merge over cosmic time, and when two galaxies collide, their central black holes can merge as well. This process, repeated over multiple mergers, could theoretically build a very large black hole in stages. Each merger adds mass, and over billions of years, the black hole grows in steps rather than continuously. For TUN 618, This scenario faces severe challenges. To reach 66 billion solar masses, an extraordinary number of mergers would have to occur in rapid succession. Each merger requires time for the black holes to spiral together, interact with surrounding stars and gas, and coalesce into a single mass. In the early universe, there simply would not have been enough massive galaxies close enough to merge at the rate required. Galaxy merger cascades, while a mechanism for growth in some supermassive black holes, are far too slow and infrequent to explain Ton 618's extreme mass in the available time. Finally, scientists consider the possibility of primordial black hole seeds. In this scenario, density fluctuations in the very early universe could produce black holes directly before stars or galaxies formed. Primordial black holes could, in principle, start with a much larger mass than stellar or direct collapse seeds. They would provide a head start in building supermassive black holes. The challenge with this idea is that there is no direct evidence linking Ton 618 to a primordial origin. Observations of quasars and black holes at high redshift do not show characteristics that clearly point to primordial formation. Additionally, the distribution of density fluctuations required to form such massive primordial black holes is not supported by current cosmological data. While theoretically possible, this scenario remains speculative, and no direct observation confirms that Ton 618 formed this way. Each of these growth models, Super-Eddington accretion, direct collapse seeds, runaway mergers, galaxy merger cascades, and primordial seeds, offers a piece of the puzzle. Each is grounded in established physics and simulations, yet none alone can account for Ton 618. Super-Eddington accretion increases growth rates but cannot sustain them long enough. Direct collapse seeds provide a large starting mass but still fall short by billions. Runaway mergers and galaxy mergers are too slow. Primordial seeds have no observational support. Ton 618 forces astrophysicists to confront the limits of each of these models. The combination of extreme mass, early formation, and rapid growth challenges everything known about black hole evolution. Standard equations fail to produce a black hole this large in the early universe, no matter which mechanism is applied. It sits at the edge of what physics allows, a reminder that the cosmos sometimes produces objects that defy expectations. The Eddington limit, central to all growth scenarios, remains a core obstacle. All accretion-based models, Super-Eddington or not, must grapple with radiation pressure. Material falling too fast should be expelled, yet Ton 618 continues to exist. The direct collapse scenario shows that large initial mass helps but does not solve the timing problem. Mergers can accelerate growth but cannot reach the required speed. Primordial seeds, while intriguing, remain unverified. In combination, these models illuminate why Ton 618 is impossible to explain fully with classical astrophysics. Ton 618 also illustrates the interplay between black holes and galaxies. Any model for its growth must account for the supply of matter. The surrounding environment had to be rich enough to feed a black hole continuously without exhausting the gas or stars. Dense star clusters and galaxy mergers attempt to explain this supply, but the scales and timelines do not match observations. The quasar is already too massive, and the host galaxy remains invisible. Each growth scenario bumps up against a hard physical limit, yet the black hole persists. The failures of these models highlight gaps in our understanding of the early universe. Ton 618 appears when the universe was only a fraction of its current age, yet its mass is extreme. Accretion-based theories struggle with radiation pressure and efficiency. Merger-based theories struggle with time and frequency. Direct collapse and primordial seeds face limits in mass and evidence. Ton 618 remains outside what current physics predicts, a singular object that challenges the assumptions underlying black hole formation. Even when combining models, the problem persists. Super-Eddington accretion could work alongside a direct collapse seed, but the required conditions, continuous uninterrupted feeding at extreme rates, remain improbable. Runaway mergers and galaxy mergers add mass, but cannot keep pace with the rate necessary for a 66 billion solar mass black hole. No combination of mechanisms fully solves the puzzle. TON 618 occupies a regime beyond which known models function, testing the edges of cosmic physics. Observations of TON 618 provide the only constraints. Its luminosity, inferred mass, and redshift set hard limits on what growth scenarios can accomplish. The quasar outshines any galaxy it resides in, demonstrating that the accretion disk is active and radiating enormous energy. This implies that feeding is ongoing or recently occurred. Yet the rate of feeding required for classical models to reach 66 billion solar masses remains beyond what the early universe could realistically provide. The numbers simply do not align. TON 618 is, in many ways, the ultimate stress test for black hole growth theories. Super-Eddington accretion is pushed to its limit. Direct collapse seeds are stretched to their maximum. Runaway mergers and galaxy merger cascades are compressed to impossible timelines. Primordial seeds are invoked without evidence. Each theory provides partial insight, but none fully explains the quasar's mass, luminosity, and early formation. TON 618 forces the question, are there growth mechanisms we have not yet discovered? Could early universe conditions allow sustained Super-Eddington accretion? Are there environmental factors that could accelerate mergers beyond predicted rates? TON 618, an extreme statistical outlier, a 1 in a trillion object that stretches physics to its limits. The light problem, TON 618, is too bright. TON 618 is one of the brightest objects in the known universe. Its light is so intense that it outshines entire galaxies. While most black holes, even supermassive ones, are invisible without surrounding material to radiate energy. TON 618 is a beacon across billions of light years. Its accretion disk emits more energy than anything nearby, creating a luminosity that both fascinates and confounds scientists. Luminosity is the total amount of energy emitted by an object per second. For stars, it is measured in units relative to our Sun. For galaxies, luminosity comes from the combined light of billions of stars. But TON 618's brightness is in a completely different league. Its accretion disk alone releases hundreds of trillions of times more energy than the Sun. It radiates across the electromagnetic spectrum, from X-rays to visible light to radio waves. The brightness of TON 618 creates a fundamental paradox. The amount of light it emits is directly tied to the rate at which matter falls into the black hole. In simple terms, the energy comes from gravity. Matter falling toward the black hole is accelerated to near-light speeds, heated to millions of degrees, and converted into radiation. There is a predictable relationship between mass growth and luminosity, determined by the physics of accretion. This is called the accretion efficiency, and it sets an upper limit on how bright a black hole can be for a given feeding rate. For most quasars, the math works. Their feeding rate matches the luminosity they emit, and both obey the Eddington limit, the point where radiation pressure balances gravity. Beyond this point, the black hole cannot accrete more matter without blowing it away. TON 618, however, violates this principle. Its observed luminosity is far higher than what would be expected for its estimated mass growth rate. In other words, the black hole is shining too brightly for the amount of matter it can reasonably consume. The accretion disk of TON 618 is the source of this extreme light. It forms from gas and dust spiraling toward the black hole, heating up due to friction and gravitational compression. The inner regions of the disk reach millions of degrees Kelvin, producing high-energy radiation, particularly in X-rays. The outer regions emit ultraviolet and visible light, contributing to the quasar's overall brightness. Because of the mass of TON 618, the disk should have a maximum luminosity based on classical accretion physics. Observations show that it is glowing near or above that limit. One way to understand the problem visually is to think of a black hole as a cosmic engine. Matter falls in, converting gravitational potential into kinetic energy, which turns into heat and radiation. There is a maximum throttle. The black hole cannot convert more mass to light than physics allows without pushing the material away. TUN 618's engine is revving far beyond that throttle. The energy output suggests that either the black hole is consuming more matter than we can see, or that the physics of accretion behaves differently at extreme scales. To break this down with numbers, consider that the Eddington luminosity sets a theoretical cap on brightness. The Eddington limit is proportional to the mass of the black hole. For a black hole of tens of billions of solar masses like TUN 618, the limit is staggeringly high, yet the observed luminosity of the quasar approaches or even exceeds this theoretical maximum. This means that the black hole is radiating energy at a rate that should make it impossible for it to continue eating at the same pace. The material falling in should be blown away, creating a self-limiting system. But TUN 618 does not appear to be slowing down. The discrepancy between expected feeding rate and luminosity creates a light problem. If the black hole were accreting matter at a normal rate, its accretion disk should be significantly dimmer. If it were producing the observed luminosity at the expected efficiency, the black hole would be consuming matter far faster than the available gas supply. Neither scenario fully resolves the paradox. The result is a quasar that is too bright for the laws of physics as we understand them. The math behind this problem can be explained narratively. Imagine calculating the energy released per second by matter falling into a black hole. The formula accounts for the mass accretion rate and the efficiency of converting that mass into radiation. For a typical supermassive black hole, the efficiency is between 10% and 40%. For TUN 618, given its observed luminosity, the mass accretion rate implied would be enormous, enough to feed tens of thousands of suns per year. This is an extraordinary demand, far exceeding what nearby galaxies could provide in gas and dust. At the same time, sustaining this accretion rate presents another challenge. Black holes do not exist in empty space, they rely on their environment. The host galaxy, gas clouds, and interstellar medium all supply material. TUN 618's host galaxy is almost invisible due to the quasar's brightness. This means that the reservoir of matter available to feed the black hole cannot be directly measured. Yet the brightness implies continuous feeding at extreme rates. Scientists are left with a paradox. The black hole shines as though it is being fed by a galactic buffet, but the surrounding galaxy appears faint or even absent. The luminosity also affects observational measurements. When a quasar shines this brightly, it overwhelms any light from nearby stars. Spectroscopic studies detect only the emission from the accretion disk, making it difficult to understand the quasar's environment. This limits scientists' ability to measure the true mass of the black hole, the amount of surrounding matter, and the dynamics of accretion. TUN 618's brightness is so extreme that it distorts the normal methods of studying quasars. The problem extends into relativistic effects near the black hole. The inner accretion disk emits light from regions moving at significant fractions of the speed of light. These high velocities produce Doppler shifts, altering the observed spectrum of the radiation. Gravitational redshift further modifies the light as photons climb out of the intense gravity well. For TUN 618, these effects are amplified because the mass is so large. The radiation reaching Earth carries the imprint of both extreme speed and gravity, providing evidence for the black hole's size and luminosity, but also complicating calculations of feeding rates. Another way to see the problem is to compare TUN 618 to other luminous quasars. Most quasars at similar redshifts have luminosities far below TUN 618, consistent with their black hole mass and expected accretion rates. TUN 618 stands out because it emits far more light than its peers. This is not a small discrepancy, it is a factor of tens or hundreds in some wavelength bands. Classical accretion physics cannot easily explain why this quasar is so far above the expected luminosity curve. The brightness also limits theories about the host galaxy. In normal galaxies, black hole growth and star formation are linked. Gas accreted onto the black hole is the same material that could form stars. Ton 618's luminosity suggests that an enormous amount of gas must be falling in. If this were true, the galaxy should have been forming stars at a corresponding rate, making it more visible. Instead, the quasar dominates all observable light, masking any evidence of star formation or galactic structure. This discrepancy between expected galactic luminosity and observed quasar brightness deepens the paradox. Ton 618's accretion disk is a physics laboratory at extreme scales. The brightness implies temperatures of millions of degrees, generating X-rays and ultraviolet radiation that radiate across space. The inner disk alone is capable of converting matter to energy with unprecedented efficiency. This raises questions about whether our models of disk physics, radiation transport, and energy release are complete. Standard accretion theory predicts certain energy outputs for given mass inflows. Ton 618 exceeds these predictions, suggesting there may be mechanisms at play that are not fully understood, such as anisotropic radiation, photon trapping, or previously unmodeled disk instabilities. Super-Eddington accretion is often invoked as a partial solution. In this scenario, some of the radiation escapes along narrow funnels perpendicular to the disk, allowing the black hole to continue accreting faster than the classical Eddington limit. While this can increase growth rates and apparent brightness in simulations, it still cannot fully account for Ton 618's luminosity over cosmic timescales. The amount of matter required to sustain such brightness continuously would still exceed the plausible supply from the surrounding environment. Ton 618 is also a visual paradox. At billions of light-years distance, its light reaches us across space that has expanded significantly. The brightness we observe represents the total energy output of the quasar at a time when the universe was less than a quarter of its current age. Even accounting for distance and redshift, the energy emitted is staggering, dwarfing everything nearby. The quasar's luminosity cannot be reconciled with the expected mass growth under standard physical laws. The mathematical relationship between mass accretion and luminosity can be described simply. Luminosity equals the mass accretion rate multiplied by the energy conversion efficiency and the square of the speed of light. For Ton 618, applying the observed luminosity produces a mass accretion rate that is difficult to supply naturally. The galaxy would need to channel enormous amounts of matter into the black hole continuously. The scale of this feeding process is unprecedented, which is why astronomers call it the light problem. The quasar's brightness also has implications for the broader universe. Ton 618 contributes significant energy to its surroundings, affecting intergalactic gas and potentially influencing the formation of nearby galaxies. Its luminosity creates powerful radiation fields, photoionizing surrounding material and heating gas clouds. These effects extend far beyond the black hole itself, creating a cosmic footprint that is disproportionately large compared to its host galaxy. The quasar is both massive and disruptive, emitting energy that shapes its environment in ways that challenge classical understanding. Even relativistic beaming, which can amplify observed brightness along the direction of a jet, does not fully resolve the light problem. Ton 618's luminosity is measured across multiple wavelengths and directions, indicating that the extreme brightness is not an observational artifact, but an intrinsic property of the accretion disk. The light is too intense, too sustained, and too widespread to be explained by orientation effects alone. Inside the accretion disk, Ton 618 is a black hole that defies everything scientists thought possible, and at the heart of its mystery lies its accretion disk. This disk is not just a collection of gas and dust. It is an engine operating on a scale almost impossible to comprehend. The disk converts matter into light with unmatched efficiency, producing the luminosity that makes TON 618 visible across billions of light years. To understand this cosmic powerhouse, we must explore the physics of the disk's inner edge, the behavior of plasma, the role of magnetic fields, and the mechanisms that keep it stable despite its colossal scale. The inner edge of the accretion disk is a region of extreme conditions. Here, matter spirals inward at velocities approaching the speed of light, forming a thin but intensely hot layer of plasma. Temperatures reach millions of degrees Kelvin, producing X-rays and ultraviolet radiation that dominate the quasar's energy output. The gravitational pull is immense, and the curvature of space-time becomes pronounced. In these inner regions, even small variations in density or pressure can have enormous effects, making the physics both complex and extreme. Plasma behavior is central to understanding the disk. Unlike ordinary gas, plasma is fully ionized, meaning electrons are stripped from atoms, creating a soup of charged particles. These particles interact with magnetic fields, which thread through the disk, producing turbulence, jets, and heat. The combination of high temperature, rapid rotation, and magnetic fields generates magnetohydrodynamic instabilities, which are responsible for transporting angular momentum outward. This allows matter to spiral inward toward the black hole, while the disk maintains a degree of stability despite the enormous forces at play. Turbulence in the disk is not random. It is structured by the interplay of gravity, rotation, and magnetic forces. Magnetic fields act as invisible scaffolding, channeling energy and influencing the flow of plasma. Instabilities like the magneto-rotational instability create friction within the disk, heating the material and allowing angular momentum to be carried away. This process enables matter to move inward while releasing energy in the form of radiation, sustaining the quasar's luminosity. The sheer size of TON 618's accretion disk adds another layer of complexity. With a black hole mass estimated at 66 billion solar masses, the disk spans distances that dwarf our solar system. The inner edge may be measured in billions of kilometers, while the outer regions extend across light days or even light weeks. Despite these scales, the disk remains coherent, maintaining a balance between gravitational forces pulling inward and pressure and radiation pushing outward. This balance is critical, allowing the disk to function as a sustained energy engine rather than fragmenting or dispersing under its own weight. Plasma dynamics are further complicated by relativistic effects near the black hole. As matter approaches the event horizon, velocities become relativistic, and time dilation affects the perception of movement and energy. Magnetic fields twist and stretch, creating jets that can channel material away from the disk at nearly the speed of light. These jets, while relatively narrow compared to the disk itself, carry a significant fraction of the energy, contributing to the quasar's overall luminosity and influencing the surrounding interstellar medium. The accretion disk also converts gravitational energy into thermal energy with remarkable efficiency. As matter falls deeper into the black hole's potential well, gravitational potential energy is converted into heat. The inner regions, being closest to the event horizon, reach the highest temperatures and radiate the most energy. For TON 618, this means the inner disk is a furnace producing more light than entire galaxies. The energy conversion is so efficient that only a fraction of the infalling mass contributes to the black hole's growth, with the rest released as radiation. Stability in the disk is maintained by a delicate balance of forces. Gravity pulls matter inward, pressure from the heated plasma pushes outward, and magnetic fields channel energy and momentum. Radiation pressure, which grows with luminosity, must also be accounted for. In smaller black holes, radiation can destabilize the disk, causing eruptions or jets. In TON 618, the immense scale allows radiation pressure to be distributed over a vast area, preventing catastrophic instability and allowing continuous accretion. The disk, therefore, operates in a regime where forces are balanced across scales, unimaginable in smaller systems. Viscosity within the disk plays a crucial role. It allows angular momentum to be transported outward, enabling matter to spiral inward. In classical fluids, viscosity arises from molecular collisions, but in the accretion disk, it is dominated by magnetohydrodynamic turbulence. This turbulence effectively acts as a viscosity, providing the friction needed to convert kinetic energy into heat. The result is a self-sustaining cycle. Matter falls inward, friction heats the disk, energy is radiated, and angular momentum is transported outward, allowing the process to continue over millions of years. The magnetic fields threading the disk also explain the formation of relativistic jets. As plasma moves through twisted magnetic field lines, energy can be funneled along the poles of the black hole. These jets can extend for thousands of light years, carrying energy away from the disk and affecting the surrounding environment. While TUN 618's jets are not fully resolved in observations, their presence is inferred from the disk's luminosity and the physics of angular momentum transport. The jets represent a channel through which the black hole can regulate its growth, expelling some energy while allowing accretion to continue. Turbulence and magnetic fields also help stabilize the disk against fragmentation. Without these forces, the disk's own gravity could cause it to collapse into clumps, leading to star formation within the disk, rather than feeding the black hole. In TUN 618, the scale of the disk ensures that pressure and magnetic support dominate over self-gravity in most regions, allowing matter to flow smoothly inward. The result is a continuous engine, converting mass into energy at rates that dwarf almost any other known system. The inner edge of the disk is particularly extreme. Matter orbits at nearly the speed of light, producing Doppler shifts and relativistic beaming. Radiation emitted from these regions is not isotropic. It is enhanced in the direction of motion. Observed from Earth, this contributes to the quasar's extraordinary brightness. Time dilation also plays a role. From the perspective of an outside observer, processes near the inner edge appear slowed, while the energy output remains immense. This combination of relativistic effects, extreme temperatures, and magnetic turbulence makes the inner disk a unique laboratory for high-energy astrophysics. The outer disk, while cooler, is also critical. It acts as a reservoir, supplying matter to the inner regions over long timescales. Gas clouds, dust, and even remnants of disrupted stars feed the outer disk, which then transports matter inward. The outer regions radiate primarily in optical and ultraviolet wavelengths, contributing to the total luminosity observed. Despite being less energetic than the inner disk, these regions are essential for sustaining accretion over cosmic timescales. TUN 618's disk may be one of the largest energy engines in the universe. By converting matter into light with such efficiency, it creates a beacon visible across billions of light years. Its size, temperature, luminosity, and stability make it an extreme example of accretion physics. The balance of plasma, turbulence, magnetic fields, and relativistic effects allows the disk to function as a coherent system rather than fragmenting under the enormous forces involved. The combination of these factors, plasma physics, magnetic field dynamics, relativistic motion, radiation pressure, and turbulence, explains how the disk can sustain extreme luminosity without collapsing. Each element contributes to the overall stability of the system, allowing TUN 618 to continue accreting matter and converting it into energy. The accretion disk is not a static structure. It is a dynamic, evolving engine that channels gravitational potential energy into radiation efficiently and continuously. Relativistic jets, while small compared to the disk itself, serve as energy release valves. They carry angular momentum and energy away from the disk, preventing local instabilities from disrupting accretion. The jets also illuminate surrounding gas, creating extended emission regions detectable across intergalactic space. In this way, the disk not only fuels the black hole's growth, but also shapes its environment, influencing matter and energy far beyond its immediate vicinity. Magnetohydrodynamic simulations of massive accretion disks support this picture. In such simulations, turbulence and magnetic fields interact to transport angular momentum outward, allowing matter to spiral inward at high rates. Energy released by friction heats the plasma to millions of degrees, producing X-rays, ultraviolet light, and optical emission. For a black hole of ton 618's mass, these simulations predict luminosities consistent with observations, demonstrating that the disk is capable of operating as a stable, extremely efficient engine. Temperature gradients in the disk also contribute to stability. The inner regions are extremely hot, generating high-energy radiation, while the outer regions remain cooler, emitting lower-energy light. This gradient allows the disk to radiate energy without overheating any single region. Pressure, magnetic forces, and viscosity work together to maintain a steady flow of matter, preventing catastrophic eruptions or disk fragmentation. The scale of ton 618's accretion disk is unmatched. Its radius extends far beyond the orbit of Pluto, while the inner edge lies perilously close to the event horizon. Within this space, matter undergoes extreme acceleration, heating, and radiation, producing a luminosity that dominates the host galaxy and can be observed across billions of light years. The combination of size, energy, and stability makes it a unique cosmic engine, demonstrating physics at extremes that challenge laboratory experiments and even theoretical understanding. The magnetic field structure is critical to maintaining coherence. Field lines twist and reconnect, generating turbulence that distributes energy and angular momentum across the disk. Without this mechanism, the disk would quickly fragment, leading to localized star formation or chaotic flows. The interplay of magnetic fields, plasma, and gravity ensures that matter continues to spiral inward, feeding the black hole and powering the quasar's luminosity. Even at these extremes, the disk remains a fundamentally predictable system. The laws of physics that govern plasma, magnetism, and relativity apply, but they operate at scales far beyond anything observed elsewhere. The inner edge, plasma dynamics, magnetic turbulence, and relativistic effects combine to create a self-regulating system capable of sustaining enormous luminosity over millions of years. Ton 618's accretion disk is, in every sense, an engine on the largest scale imaginable. How big is ton 618? Ton 618 is not just a black hole. Its mass is estimated at around 66 billion times the Sun, which immediately suggests a size that challenges human comprehension. To understand just how vast ton 618 is, it helps to compare it to familiar objects in our own solar system: the Sun, the orbit of Saturn, and even the distance traveled by Voyager 1. These comparisons allow us to grasp the size of its event horizon and the immense reach of its gravitational influence. The Sun, our local standard of mass and size, has a radius of approximately 696,000 kilometers. For an average supermassive black hole like Sagittarius A** at the center of the Milky Way, with a mass of about 4 million solar masses, the event horizon, or Schwarzschild radius, is roughly 12 million kilometers. This is already a staggering number, but ton 618 dwarfs even this. With tens of billions of solar masses, its event horizon extends over 100 times larger than that of Sagittarius A*, reaching scales that encompass regions of our solar system. To place ton 618 in a context we can visualize, consider Saturn. Saturn orbits the Sun at an average distance of about 1.43 billion kilometers, or 9.5 astronomical units. If ton 618 were located at the center of our solar system, its event horizon alone would stretch beyond Saturn's orbit, enveloping the gas giant and filling the inner solar system. Earth, Mars, and Jupiter would be well within the reach of its gravitational pull at this scale, illustrating the enormous scale of the black hole's physical presence. Even Voyager 1, humanity's farthest traveling spacecraft, provides a useful benchmark. Voyager 1 has traveled more than 23 billion kilometers from the Sun, crossing beyond the edge of the heliosphere into interstellar space. Ton 618's Schwarzschild radius, when scaled to the Sun, reaches distances approaching Voyager 1's journey. While Voyager 1 moves through the emptiness of interstellar space, TON 618's event horizon is a solid measure of the gravitational boundary that nothing, not even light, can escape. The comparison emphasizes that this is not just a massive object, it is a structure whose sheer size extends across distances comparable to those reached by our most ambitious probes. The event horizon is defined by the Schwarzschild radius, which is proportional to the black hole's mass. For TON 618, this radius measures hundreds of billions of kilometers. To put it into perspective, Pluto orbits the Sun at an average distance of roughly 5.9 billion kilometers. TON 618's horizon would extend far beyond Pluto, encompassing the inner and outer planets with room to spare. The entire solar system as we know it would fit inside its event horizon, with the Sun at the center, replaced by this cosmic giant. If we simulate the idea that TON 618 replaced the Sun, we can calculate its Schwarzschild radius and compare it to planetary distances. The Sun's radius is about 0.005 astronomical units. TON 618's radius, by contrast, is measured in hundreds of astronomical units, far larger than the distance from the Sun to Neptune, which is around 30 astronomical units. The visual alone illustrates the magnitude. The black hole would not just occupy the solar system, it would engulf it multiple times over. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and even the distant Kuiper Belt objects would all be well within its event horizon. The gravitational boundary of TON 618 would dominate any local stellar system in ways that completely eclipse ordinary scales. The calculation of the event horizon is simple in principle. The Schwarzschild radius is given by the formula. Where is the gravitational constant, is the mass of the black hole, and is the speed of light. For TON 618, with a mass of 66 billion solar masses, the result is approximately 195 billion kilometers. This distance is equivalent to about 1,300 astronomical units. By comparison, Voyager 1 has traveled only about 158 astronomical units from the Sun. TON 618's event horizon stretches far beyond the furthest reaches of any object humanity has sent into space. The scale is not linear in human terms. The Sun's mass and radius are familiar. We can see the Sun in the sky and experience its energy. Scaling up to TON 618 removes all familiar reference points. Saturn's orbit, Voyager 1, Pluto, even the Kuiper Belt, all fit comfortably inside a single gravitational boundary of this black hole. Its size forces a new level of imagination, a structure whose boundary is measured in thousands of times the radius of the Sun, swallowing distances that in human experience are astronomical. The event horizon represents the limit where escape velocity equals the speed of light. Inside this boundary, nothing can escape. Not light, not matter, not information. For TON 618, this radius is so large that if the black hole replaced the Sun, the boundary would stretch beyond every planet's orbit in our solar system, even encompassing distant dwarf planets. The familiar layout of the solar system becomes meaningless in this context. Distances measured in astronomical units, kilometers or light hours, are entirely contained within a single singular object. Even when considering the volume inside the event horizon, TON 618 is mind-boggling. The volume scales with the cube of the Schwarzschild radius, meaning it is not just hundreds of times larger in distance, but billions of times larger in volume than the Sun. The mass is concentrated, but the space it occupies in gravitational influence is vast. The density of such a supermassive black hole is low compared to stellar mass black holes, but the total mass is unimaginable. Its gravitational effects dominate everything within the solar system scale, and its presence would redefine familiar planetary orbits. The Sun, by comparison, is tiny. Its radius is just a fraction of an astronomical unit. Saturn orbits nearly 10 astronomical units away. Voyager 1 has traveled more than 150 astronomical units. TON 618's radius, over 1,300 astronomical units, absorbs all these scales. Any planetary system placed inside it would be engulfed within its gravitational boundary. The familiar concept of orbit loses meaning at this scale. Objects would spiral toward the event horizon in ways consistent with general relativity, accelerated to extreme velocities and heated to high energies before crossing the point of no return. If we extend this thought experiment further, we can visualize what the solar system would look like inside TON 618's horizon. The Sun's energy output would be irrelevant, replaced entirely by the black hole's accretion disk radiation. Planets would no longer orbit a central star in the conventional sense. Instead, they would be drawn inexorably toward the singularity, their trajectories dictated by space-time curvature. The size comparison is extreme. Mercury and Neptune, separated by billions of kilometers, would both lie comfortably within a single Schwarzschild radius. Even Voyager 1, humanity's most distant object, would be deep inside the gravitational pull of the black hole. To understand the scale further, consider the distance from the Sun to the Kuiper belt, roughly 50 astronomical units. TON 618's event horizon is more than 20 times that distance. Its outer boundary, the last region where gravity would prevent light from escaping, extends well beyond the solar system's limits. The black hole dominates a volume that, in terms of human reference points, is unimaginably large. Any orbiting object, whether planetary, asteroidal, or a distant spacecraft, would be within the sphere where the black hole's gravity dictates motion. Astronomers often use the Schwarzschild radius to convey black hole size, but in practice, the physical manifestation is the accretion disk and surrounding structures. For TON 618, the disk itself is enormous, likely extending millions of kilometers in radius. But the event horizon defines the ultimate boundary. The comparison with our solar system shows that the scale is not abstract. It is comparable to multiple orbital radii combined. The black hole is so massive that standard planetary scales shrink in comparison. To put TON 618 into perspective, consider the distance light travels in a day, roughly 26 billion kilometers. The Schwarzschild radius of TON 618 spans multiple light days. Signals, radiation, and matter crossing its event horizon do so over distances that dwarf familiar solar system scales. Even the farthest planets, thousands of times the Sun's radius away, lie deep within this boundary. The scale emphasizes that TON 618 is not just large. It is a structure that redefines what it means to measure distance in astrophysical terms. Finally, the comparison with Voyager 1 is striking. Humanity has reached 158 astronomical units from the Sun, a remarkable achievement over decades of spaceflight. TON 618's event horizon, by contrast, extends over 1,300 astronomical units. Our most distant spacecraft would be almost insignificant, deep inside the gravitational sphere of a single cosmic object. The numbers demonstrate the extreme nature of TON 618, a black hole whose sheer size challenges our ability to relate to even the farthest reaches of the solar system. The observation challenges. Why we can't study it clearly. TON 618 sits at a distance of approximately 10.8 billion light-years from Earth. To put that in perspective, the light reaching our instruments today left TON 618 when the universe was only a fraction of its current age. Observing something this distant is already a challenge because the further away an object is, the fainter and redshifted its light becomes. Light from TON 618 travels across vast stretches of expanding space, stretching into longer wavelengths as it does so. This redshift means that light emitted in ultraviolet or visible bands reaches us in infrared, requiring highly sensitive instruments to even detect it. The quasar itself compounds the problem. TON 618 is not a quiet black hole emitting occasional bursts of energy. It is a hyper-luminous quasar, radiating energy far beyond its host galaxy. The brightness of the quasar overwhelms almost every instrument used to study it. Even the most powerful ground-based and space-based telescopes struggle to separate light from TON 618 from any surrounding material. The quasar's light is so intense that it drowns out the faint glow of stars, gas clouds, and other structures that might otherwise provide context. Observers are left with the quasar itself dominating the data, with little to no information about the galaxy it inhabits. Limited resolution is another major obstacle. Telescopes, no matter how advanced, have finite resolving power, determined by their aperture size and observing wavelength. Even instruments like the Hubble Space Telescope and the James Webb Space Telescope face constraints. TON 618's light has traveled across billions of light-years, spreading and dimming along the way. The angular size of its host galaxy, even if it were visible, would appear minuscule on the sky, smaller than a pixel in most instruments. The quasar's luminosity further blurs any underlying structures, effectively masking everything around it. Spectral analysis remains the primary tool astronomers have to study TON 618. By analyzing the quasar's light at different wavelengths, scientists can infer properties like the black hole's mass, the temperature and composition of its accretion disk, and the velocity of gas orbiting near the event horizon. Spectra reveal the signatures of broad emission lines, particularly from hydrogen and ionized elements, which are Doppler broadened due to the extreme velocities near the black hole. These lines allow mass estimates using techniques like the virial method, providing one of the few ways to understand the black hole's scale and behavior. Even spectral analysis comes with uncertainty. The light from TON 618 is redshifted into the infrared, where Earth's atmosphere is opaque in many bands, requiring space-based instruments. Absorption along the line of sight from interstellar and intergalactic gas alters the observed spectrum, complicating measurements. Instrumental limitations, calibration errors, and the need to model underlying physics contribute further to uncertainty. While scientists can estimate mass and luminosity with impressive precision, these values come with significant error margins. Distance introduces additional challenges. TON 618 is located so far away that we are observing it as it existed more than 10 billion years ago. Any measurement reflects not the current state of the black hole, but a snapshot from the early universe. This complicates comparisons to nearer quasars or black holes, which may have evolved significantly since that epoch. Even if instruments could resolve fine details, the fact that we are looking back in time means that some features may not exist today, and some observed properties may be influenced by conditions unique to the early universe. The quasar's brightness also creates observational paradoxes. TON 618 outshines its host galaxy by such a large factor that astronomers struggle to measure the galaxy's mass, size, or structure. Normally, a supermassive black hole sits in the center of a galaxy, and the dynamics of surrounding stars provide clues to its mass and environment. For TON 618, the light from the accretion disk and relativistic jets dominates any potential stellar or gas emission, making direct observation impossible. The host galaxy appears nearly invisible against the quasar's glare, limiting our understanding of how the black hole interacts with its environment. Limited resolution is not just a matter of pixels, it affects physical interpretation. Features smaller than the telescope's resolving power are blurred together, creating uncertainties in models of accretion, jet formation, and energy output. For a black hole like TON 618, the inner accretion disk and base of the jets are critical for understanding its physics, but they occupy regions far smaller than any current instrument can resolve directly. Scientists rely on indirect methods like light curve variability, spectral line widths, and relativistic Doppler shifts to infer conditions near the event horizon. These methods are powerful but inherently indirect, introducing potential biases and assumptions into models. Another challenge comes from the interstellar and intergalactic medium. Light from TON 618 travels through billions of light-years of space, passing through gas, dust, and cosmic structures. Each layer absorbs or scatters certain wavelengths, creating features in the observed spectrum that are unrelated to the black hole itself. Disentangling intrinsic properties from intervening absorption requires careful modeling and introduces uncertainty into measurements of luminosity, mass, and accretion rate. Even the most sensitive instruments face limits in signal-to-noise ratio. Ton 618's flux, although extraordinarily high, is spread across an enormous range of wavelengths and arrives at Earth extremely diluted due to the vast distance. Detectors must integrate light over long periods to collect enough photons for meaningful analysis. Variations in the quasar's output, which can occur over days, months, or years, complicate the interpretation. Because of these factors, measurements must be averaged or modeled over time, introducing additional layers of uncertainty. Time variability presents both a challenge and an opportunity. Ton 618's brightness is not perfectly steady. The accretion disk exhibits fluctuations in intensity due to turbulence, magnetic instabilities, and variations in accretion rate. Observing these changes provides clues about the inner disk and relativistic processes, but also requires instruments to distinguish intrinsic variability from instrumental noise and intervening absorption. Long-distance light travel further complicates interpretation, as light from different parts of the disk may arrive at slightly different times due to relativistic effects. The distance also limits multi-wavelength observations. Ton 618 emits across the electromagnetic spectrum, from X-rays to radio waves. Each wavelength band requires specialized instruments with different resolutions and sensitivities. Coordinating observations across multiple bands is challenging, especially for an object so far away. Some wavelengths are absorbed by Earth's atmosphere, necessitating space-based telescopes that may have limited availability. This creates gaps in coverage, limiting the ability to construct a complete picture of the quasar's energy output and dynamics. The quasar's redshift introduces another layer of complexity. At a redshift of around 2.2, the rest frame ultraviolet light from the accretion disk is shifted into the infrared. Observations in this band are technically challenging, requiring instruments cooled to extremely low temperatures to detect faint infrared photons. Even with state-of-the-art instruments like the James Webb Space Telescope, resolution is limited by diffraction and detector sensitivity. The combination of distance, redshift, and overwhelming brightness makes Ton 618 an observational extreme. The limited ability to resolve the quasar's host galaxy creates uncertainties in understanding black hole galaxy coevolution. Supermassive black holes are thought to grow alongside their host galaxies, but for Ton 618, the host remains largely hidden. Without clear observations of surrounding stars and gas, astronomers cannot measure the galaxy's mass or determine whether it has structural features like a bulge or spiral arms. The quasar's light dominates all visible and infrared signals, effectively creating a one-object system where the galaxy is almost invisible. Interferometry, a technique that combines light from multiple telescopes to achieve higher resolution, offers some hope but is still limited. The scales involved with Ton 618 are so large that even interferometers struggle to resolve inner structures. For example, radio interferometry can trace jet structures, but cannot directly image the inner accretion disk or precisely measure event horizon scales. Optical and infrared interferometry face similar limits due to photon dilution over extreme distances. The combination of brightness, distance, and angular size makes direct imaging virtually impossible with current technology. Spectroscopy remains the backbone of analysis. Broad emission lines from ionized gas reveal the velocity of material orbiting the black hole, allowing mass estimates using the virial theorem. By measuring Doppler shifts and line widths, scientists can infer the speed of matter near the accretion disk and extrapolate the black hole's gravitational influence. These indirect measurements are powerful, but rely on assumptions about disk geometry, inclination, and emission mechanisms. Variations in these parameters introduce uncertainties, and the extreme brightness of the quasar can skew line profiles, complicating analysis. Even advanced techniques like reverberation mapping, which measures time delays between variations in continuum emission and response in emission lines, are limited by distance and signal strength. TON 618's light travel time and redshift stretch observed variability, making it difficult to resolve fast processes in the inner accretion disk. The quasar's overwhelming brightness can also mask subtle variations in emission from surrounding gas, reducing the accuracy of these measurements. The combination of all these factors, distance, luminosity, redshift, instrumental limits, and intervening absorption, creates a situation where TON 618 is observed primarily as a point source with a complex spectrum. Its host galaxy, inner accretion disk structure, and detailed jet formation regions remain largely hidden. This lack of direct observational clarity imposes fundamental limits on how precisely we can understand the black hole's mass growth, feeding mechanisms, and interaction with its environment. Even with the most sophisticated simulations, astronomers must rely on models constrained by limited spectral data. Variations in line width, luminosity, and inferred temperature inform theoretical models of accretion physics, but direct confirmation is lacking. TON 618 becomes a case where observation and theory intersect under extreme uncertainty. While the quasar provides invaluable information about supermassive black holes in the early universe, its sheer distance and overwhelming light create a situation where much of its environment remains beyond direct study. TON 618 exists at the limits of what physics predicts, and its sheer size, luminosity, and age force astronomers to revisit long-standing models of black hole growth. Its mass, estimated at tens of billions of solar masses, is not just large, it is extreme in ways that classical theories of cosmic evolution struggle to accommodate. Studying this black hole does not simply provide data about one object. It challenges fundamental assumptions about how supermassive black holes and galaxies form and evolve in the early universe. The growth speed of black holes is constrained by physical limits. Classical models relying on accretion from surrounding gas and mergers with other black holes predict upper bounds on mass achievable in the universe's first few billion years. TON 618's existence at 10.8 billion light-years, when the universe was young, implies that matter must have accumulated at extraordinary rates. The black hole's mass cannot be explained by standard stellar seed models or even by direct collapse scenarios alone. Its growth demands reconsideration of the timescales and efficiency of mass accumulation. Early universe conditions play a critical role in this analysis. TON 618 provides a window into a time when galaxies were forming, gas was abundant, and density fluctuations were larger than those observed in today's universe. The presence of such a massive black hole indicates that local conditions must have allowed rapid collapse and accretion. These conditions could include unusually dense gas clouds, early formation of large dark matter halos, or efficient feeding mechanisms that bypass the usual constraints imposed by radiation pressure and the Eddington limit. TON 618 forces scientists to think in extremes. If we assume it formed from a stellar mass seed, the black hole would have had to accrete matter at Super-Eddington rates for nearly the entirety of the universe's first billion years. Even direct collapse seeds, forming from massive gas clouds of 100,000 to 1 million solar masses, fall short by billions of solar masses. The black hole's mass and age suggest that either unknown processes accelerated its growth, or that early universe conditions were far more conducive to rapid mass accumulation than current models predict. This has implications for galaxy formation as well. Black holes are typically thought to co-evolve with their host galaxies. The mass of a supermassive black hole correlates with the stellar mass and bulge properties of its galaxy. TON 618, however, appears to outgrow any plausible host galaxy by orders of magnitude. Observational limits prevent a clear view of its surrounding stars, but theoretical models suggest that if the galaxy exists, it must be unusually massive or highly compact. The black hole challenges the assumption that galaxy growth and black hole growth are always tightly coupled, especially in the early universe. high-energy astrophysics relies on benchmark objects to test the extremes of physical models. TON 618 serves as a reference point for the maximum observed black hole mass and luminosity. Its accretion disk operates at scales that dwarf almost every other known system, providing a laboratory for understanding plasma physics, magnetic turbulence, relativistic effects, and energy conversion. Models of radiation pressure, angular momentum transport, and jet formation are tested against the observable properties of TON 618. Its luminosity, line widths, and inferred disk properties are used to refine theories of quasar physics under extreme conditions. The black hole also informs studies of the early universe's density structure. Its formation implies that large-scale fluctuations in matter density existed earlier than previously thought. Such fluctuations could have created localized regions with abundant gas, enabling rapid black hole growth. TON 618's existence indicates that these conditions were not isolated, suggesting that other similarly massive black holes could have formed in the early cosmos. This has implications for the overall distribution of matter and the efficiency of structure formation in the first billion years after the Big Bang. The speed at which TON 618 must have grown also challenges assumptions about accretion efficiency. Classical accretion models suggest that as black holes accumulate mass, radiation pressure pushes against incoming matter, limiting growth rates. TON 618 demonstrates that these limits may be circumvented under certain conditions. Its accretion disk must have processed matter at extreme rates without dispersing material, highlighting gaps in our understanding of high-luminosity quasar physics. Observing TON 618 also highlights the interplay between distance, brightness, and physical inference. Located over 10 billion light-years away, it shows that massive black holes formed rapidly in the early universe. This raises questions about the timing and efficiency of cosmic evolution. If TON 618 existed so early, other massive structures, galaxies, clusters, and cosmic filaments may also have formed earlier than expected. It provides a point of calibration for simulations of early universe physics, allowing theorists to test models against a real, extreme object. The luminosity of TON 618 makes it a key benchmark for understanding energy output in quasars. Its accretion disk converts matter into radiation with remarkable efficiency, outshining entire galaxies. This extreme luminosity provides constraints on the mass inflow rates and the physics of disk stability. The black hole becomes a natural laboratory for studying the limits of radiative processes, magnetic field interactions, and relativistic phenomena. Observations of emission lines, spectral variability, and Doppler shifts from TON 618 allow astrophysicists to test theories under conditions inaccessible elsewhere. In addition, TON 618 serves as a benchmark for jet physics. Although direct imaging of its jets is limited by distance, the energy output inferred from radio observations and spectral analysis indicates highly energetic outflows. These relativistic jets provide clues about angular momentum transport and magnetic field structures in extreme accretion disks. By comparing TON 618 to closer quasars, astrophysicists can explore scaling relations between black hole mass, disk luminosity, and jet power. The black hole thus becomes a cornerstone object in understanding high-energy phenomena across cosmic history. TON 618 also challenges theoretical limits imposed by the Eddington luminosity. Classical theory predicts that radiation pressure balances gravitational pull at a maximum luminosity for a given mass. For the black hole to reach its observed mass in the early universe, it must have accreted at or above this limit for extended periods. Its observed luminosity approaches this threshold, implying highly efficient energy conversion or intermittent periods of Super-Eddington accretion. This extreme behavior provides critical constraints for models of quasar evolution and accretion physics. By forcing these reassessments, TON 618 reshapes our understanding of the early universe. It demonstrates that conditions in the first billion years could support the rapid formation of extreme objects. This has implications for models of cosmic reionization. the formation of massive galaxies, and the early distribution of dark matter. TON 618 provides a real example against which simulations of high redshift universe evolution can be calibrated, revealing whether current models can reproduce such rapid growth under plausible physical conditions. The black hole's mass and brightness also allow for a unique study of scaling relations in astrophysics. In nearby galaxies, correlations exist between black hole mass and galaxy properties, like bulge velocity dispersion and stellar mass. TON 618 lies far outside these correlations, suggesting that in the early universe, growth processes could operate independently or under different regimes than observed locally. This provides a benchmark for testing whether scaling laws are universal or epoch-dependent. TON 618 also informs the study of quasar lifetimes. Its extreme luminosity implies sustained accretion over hundreds of millions of years. Observing the quasar allows astronomers to infer how long such massive objects can maintain high energy output, how accretion rates vary, and how feedback mechanisms may regulate surrounding matter. This, in turn, affects galaxy formation and the distribution of interstellar and intergalactic gas in the early universe. By forcing scientists to reconsider growth speeds, TON 618 exposes gaps in our understanding of supermassive black hole evolution. Classical models assume growth rates limited by accretion physics and available matter. TON 618 demonstrates that, under certain conditions, these rates can be exceeded, suggesting alternative feeding mechanisms or early universe environments far denser than previously considered. Its existence provides a natural stress test for the physics governing black hole evolution. The object's properties also provide constraints on early cosmic conditions. Its mass implies that the surrounding region must have been exceptionally gas-rich, with minimal disruption from supernovae or other energetic events that could disperse material. TON 618's presence indicates that early galaxies, or protogalaxies, could support extremely high-density environments conducive to rapid black hole growth. This forces a re-evaluation of initial conditions in cosmological simulations and the timing of large-scale structure formation. TON 618 is a benchmark for energy conversion processes. Its accretion disk demonstrates how gravitational energy can be transformed into electromagnetic radiation with unparalleled efficiency. Observing this process informs models of how matter behaves under extreme gravity, high temperature, and relativistic motion. By comparing TON 618 with less massive quasars, astrophysicists gain insight into how energy output scales with black hole mass, providing a reference for the most extreme energy engines in the universe. The black hole also shapes our understanding of galaxy-black hole feedback. In nearby galaxies, black holes influence star formation, gas inflows, and overall galactic evolution. For TON 618, the host galaxy remains largely invisible, but the black hole's energy output likely affects surrounding matter. Even without direct observation, modeling its luminosity and jets allows astrophysicists to infer how such a massive black hole might regulate its environment. This informs theories of early galaxy formation and the role of feedback in shaping cosmic structures. TON 618 is more than an extreme black hole. It is a benchmark for the limits of physical models. Its mass, growth rate, and luminosity push the boundaries of what is considered possible in high-energy astrophysics. By forcing reassessment of growth speed models, challenging assumptions about galaxy formation, and providing a window into early cosmic conditions, TON 618 serves as a reference object for both theoretical and observational astrophysics. It sets standards for the extremes of black hole mass, quasar luminosity, and energy conversion efficiency. TON 618 also emphasizes the role of indirect observation. Because of distance, brightness, and instrumental limits, most of what we know comes from spectral analysis, line widths, and variability studies. Despite these constraints, the black hole provides precise benchmarks for theory. Its existence allows researchers to test models of early universe physics, accretion dynamics, and quasar behavior under extreme conditions. The black hole becomes a standard against which all other high-mass quasars are compared. The black hole's properties influence multiple areas of astrophysics, from cosmic evolution to high-energy phenomena. Its mass sets an upper bound for supermassive black hole growth observed in the early universe. Its luminosity tests the limits of radiation-driven accretion. Its age informs the timeline of cosmic structure formation. Each aspect provides a data point for refining simulations and models, making TON 618 a critical reference across astrophysical disciplines. TON 618's extreme nature also drives technological and observational advancement. To study such an object, instruments must achieve sensitivity, resolution, and wavelength coverage at unprecedented levels. Space-based infrared telescopes, high-resolution spectroscopy, and multi-wavelength campaigns are necessary to capture even indirect data. The black hole's demands push observational astronomy to its limits, providing benchmarks for instrument design and data interpretation. Its place in high-energy astrophysics is therefore not just symbolic, it is practical. TON 618 provides measurable extremes for theories of plasma physics, relativistic motion, accretion, disk stability, jet formation, and energy conversion. Every measurement of its spectrum, variability, or luminosity tests existing models. Its extreme mass and energy output ensure that any theory of black hole growth or early universe conditions must account for its existence. TON 618 sets a floor for what models must explain, and a ceiling for what is observed in terms of energy output. Finally, TON 618's continued observation informs our understanding of cosmological evolution. As telescopes and instruments improve, astronomers can refine measurements of its mass, luminosity, and spectral characteristics. Each new observation recalibrates models of early universe physics, providing a continuously evolving benchmark. TON 618 stands as a singular object that encapsulates the limits of growth, energy, and observation in the high-energy universe. Scientific mysteries that TON 618 might help solve. TON 618 is not just a hypermassive black hole, it is a living laboratory for some of the most profound questions in astrophysics. Its extreme mass, luminosity, and early appearance in cosmic history make it a key object in understanding how the universe evolved in its formative stages. Among the most compelling questions it touches on are the formation of giant galaxies, the evolution of supermassive and hypermassive black holes, and the role early quasars played in cosmic reionization. Each of these topics is deeply interconnected, and TON 618 offers a unique perspective because it represents the extreme end of black hole growth in the early universe. One of the first mysteries TON 618 illuminates is the formation of giant galaxies. In modern cosmology, galaxies form through hierarchical structure formation, where smaller clumps of matter coalesce over time into larger structures. Standard models suggest that massive galaxies grow gradually, accumulating stars, gas, and dark matter over billions of years. The existence of TON 618 complicates this picture because its mass indicates that a tremendous concentration of matter must have been present very early. For a black hole to reach tens of billions of solar masses when the universe was less than 3 billion years old, its host galaxy must have contained enormous amounts of gas and stars, far exceeding what many current models predict. This raises questions about the initial density of matter in protogalactic regions, and whether galaxy formation in the early universe could proceed faster or more efficiently under certain conditions. TON 618's mass also provides insight into the relationship between black holes and their host galaxies. In nearby galaxies, astronomers have observed tight correlations between the mass of central black holes and properties like bulge mass, stellar velocity dispersion, and overall galaxy luminosity. These correlations suggest that black holes and galaxies evolve together, influencing each other through feedback mechanisms. TON 618 challenges this assumption because its estimated mass implies a host galaxy of extraordinary scale, yet observations have failed to detect the host clearly. This discrepancy raises fundamental questions about the processes linking galaxy formation and black hole growth, particularly in the early universe. The black hole may have grown faster than its galaxy, or conditions might have allowed the black hole to dominate its surroundings without the galaxy fully forming around it. The growth of TON 618 is tightly linked to the concept of hypermassive black holes. Supermassive black holes like Sagittarius A** at the center of the Milky Way or M87* in the Virgo cluster typically reach millions to a few billion solar masses. Hypermassive black holes, of which TON 618 is an extreme example, surpass this scale dramatically. Understanding how such objects form and evolve informs broader questions about the limits of gravitational collapse, accretion physics, and energy output. In the early universe, matter was more densely packed, and cosmic structures were smaller and less mature. Yet TON 618 achieved a mass far beyond what is considered typical, even for supermassive black holes today. Studying its properties helps constrain models of mass growth, disk stability, and relativistic effects under conditions of extreme density and luminosity. Another key scientific mystery TON 618 may illuminate is the role of early quasars in cosmic reionization. Reionization occurred within the first billion years after the Big Bang, when the intergalactic medium transitioned from neutral to ionized due to radiation from the first stars, galaxies, and quasars. The energy output from massive quasars like TON 618 would have contributed significantly to this process. Its intense luminosity, particularly in ultraviolet and X-ray wavelengths, would have ionized surrounding hydrogen, influencing the evolution of nearby structures and contributing to the overall ionization of the universe. Quantifying the contribution of hyperluminous quasars helps astrophysicists model the timing, scale, and uniformity of reionization, as well as its effect on subsequent galaxy formation. TON 618 also informs our understanding of accretion physics at extreme scales. Its accretion disk, operating at millions of degrees Kelvin and radiating more energy than entire galaxies, represents the most efficient conversion of mass to energy observed in the early universe. Studying the disk's properties, including plasma turbulence, magnetic fields, and relativistic effects near the event horizon, allows scientists to refine models of how matter behaves under extreme gravity. These observations can be applied to other quasars and black holes, extending our knowledge of disk stability, jet formation, and energy transport under conditions far beyond what can be replicated in simulations or nearby objects. The black hole's jets, though difficult to resolve directly, also provide clues about high-energy astrophysics. Relativistic jets are streams of plasma ejected from the regions near the event horizon at speeds approaching that of light. These jets carry enormous amounts of energy and can influence the surrounding interstellar medium, regulating star formation and gas inflows. For TON 618, the inferred jet activity suggests that hypermassive black holes could have played a role in shaping early galaxy environments on a large scale. By comparing TON 618 to other quasars with observable jets, scientists can test how jet power scales with black hole mass and accretion rate, providing a benchmark for extreme energy output. TON 618 also challenges timelines for early cosmic evolution. If such a massive black hole existed at 10.8 billion light-years, it implies that the processes enabling rapid mass accumulation, such as direct collapse seeds, Super-Eddington accretion, or early mergers, were already in place within the universe's first billion years. This raises questions about how common these conditions were, whether other hypermassive black holes formed at similar epochs, and how these objects influenced their surroundings. TON 618 provides a critical data point for calibrating simulations of early cosmic structure formation, ensuring that theoretical models can reproduce observed extremes. The existence of TON 618 further highlights the importance of density fluctuations in the early universe. Cosmological models suggest that small initial variations in matter density led to the formation of cosmic structures over time. TON 618 implies that some regions experienced unusually high concentrations of matter, enabling rapid black hole growth. Studying these density variations informs our understanding of large-scale structure formation, including the emergence of galaxy clusters, filaments, and voids. TON 618 serves as a natural probe into these early conditions, providing constraints on the size, mass, and distribution of primordial overdensities. By observing TON 618 spectrum, astronomers can study the chemical composition of the surrounding gas. Emission lines from elements such as hydrogen, helium, and heavier ions reveal the conditions of matter near the black hole. These measurements provide insight into the early chemical enrichment of the universe, showing how the first generations of stars and supernovae influenced the interstellar medium. TON 618's extreme luminosity makes it possible to detect these spectral features across enormous distances, offering a rare window into early universe chemistry and star formation processes. TON 618 also provides a benchmark for understanding feedback mechanisms. In the local universe, black hole feedback regulates star formation, influences gas cooling, and shapes galaxy morphology. In the early universe, hypermassive black holes like TON 618 may have had an outsized influence, injecting energy into surrounding regions and potentially suppressing or enhancing the formation of nearby structures. Studying the inferred energy output, jets, and radiation environment allows scientists to model how early quasars impacted their cosmic neighborhoods, influencing the growth of other galaxies and the evolution of large-scale structure. The black hole's size and energy output also inform the study of extreme physics near event horizons. Relativistic effects such as time dilation, gravitational redshift, and frame dragging are magnified in objects of this mass. Observations of TON 618 allow for testing models of spacetime under conditions of extreme curvature. The velocity of orbiting matter, inferred from spectral line broadening, provides constraints on the gravitational potential and angular momentum of the accretion disk. These measurements extend our understanding of general relativity in the strong field regime, applying lessons from the most massive black holes in the early universe. TON 618's discovery has prompted new theoretical models of black hole and galaxy co-evolution. Its existence indicates that hypermassive black holes can form independently of fully developed galaxies, at least temporarily. This decoupling challenges classical assumptions and suggests alternative pathways for cosmic structure formation. Simulations incorporating TON 618-like objects must account for rapid mass accumulation, extreme radiation feedback, and early environmental conditions, providing a testbed for high-energy astrophysics under extreme conditions. The quasar also helps refine observational techniques. Its extreme distance and luminosity push the limits of spectroscopic analysis, requiring advanced instruments and modeling to extract meaningful information. Techniques such as Doppler broadening analysis, emission line modeling, and variability studies are applied to TON 618 to infer properties that cannot be resolved directly. Lessons learned from studying TON 618 inform strategies for observing other distant quasars, guiding telescope design, wavelength selection, and data processing for high redshift astrophysics. TON 618 also sheds light on the distribution of dark matter in the early universe. Hypermassive black holes likely reside within large dark matter halos, which provide the gravitational well necessary for rapid matter accumulation. By modeling the expected halo mass and distribution, scientists can compare TON 618's inferred growth to predictions from dark matter cosmology. This helps refine our understanding of how dark matter structures influence the formation of the first galaxies and black holes, providing a critical intersection between astrophysics and cosmology. The black hole's radiation also provides constraints on intergalactic medium properties. TON 618's light travels through billions of light years, interacting with hydrogen clouds, gas filaments, and other structures along the line of sight. Absorption features in its spectrum reveal the density, temperature, and composition of intergalactic matter in the early universe. This data complements studies of reionization, large-scale structure, and cosmic chemical evolution, making TON 618 a multi-purpose probe of early universe conditions. By studying the black hole's environment, scientists can investigate star formation rates in extreme conditions. The energy output from TON 618 would have influenced surrounding gas, potentially triggering or suppressing star formation. Observing companion structures, if detectable, and modeling energy feedback provides insights into how hypermassive black holes affect their local cosmic neighborhoods. These studies inform theories of early galaxy assembly, showing how black holes can shape the distribution and evolution of stars on a galactic scale. TON 618 also highlights the limits of classical accretion theory. Its mass, age, and luminosity suggest that standard models cannot fully explain the rapid growth observed. Super-Eddington accretion, direct collapse seeds, and early mergers provide partial solutions, but the black hole remains at the extreme edge of what is physically plausible. Its existence challenges theorists to develop new models, refine parameters, and explore previously untested mechanisms for black hole growth in the early universe. TON 618 serves as a reference for future observations. As telescopes become more powerful, astronomers can probe the quasar's jets, accretion disk structure, and host environment in greater detail. Each new measurement refines models of hypermassive black hole formation, galaxy assembly, and early universe physics. TON 618 sets the standard for what is physically possible, providing a benchmark object that pushes the boundaries of high-energy astrophysics and cosmology. TON 618's relativistic jets, streams of matter near light speed. TON 618 is not just a hypermassive black hole, it is a powerhouse of energy, and one of the most striking phenomena associated with it is the relativistic jets it produces. These jets are streams of matter propelled at velocities approaching the speed of light, extending hundreds of thousands of light years into intergalactic space. They are among the most extreme displays of physics in the universe, a combination of gravitational energy, magnetic fields, and plasma dynamics channeled into narrow beams. Relativistic jets are produced by some of the most massive black holes, but for a hypermassive object like TON 618, the scale, energy, and velocity of these jets are beyond anything observed in nearby galaxies. The formation of relativistic jets begins very close to the black hole in the inner regions of the accretion disk and the corona above it. As matter spirals inward, it heats up to millions of degrees Kelvin and forms plasma that is highly ionized. Magnetic fields, generated by the motion of charged particles in the disk, are twisted and amplified by the black hole's spin and the intense rotation of the disk. These magnetic fields act like rails, channeling some of the inflowing matter away from the disk along the black hole's rotational axis. In TON 618, the mass and angular momentum of the black hole mean that the magnetic fields can reach enormous intensities, providing the power to accelerate particles to relativistic speeds. Jets carry enormous amounts of energy. For TON 618, the energy output is comparable to, or even exceeds, the combined light of billions of stars. Most of this energy is kinetic, in the motion of the particles, but a significant fraction is electromagnetic, producing radio, optical, X-ray, and even gamma-ray emission. The jets remain collimated over vast distances, meaning that they maintain their narrow beam-like structure without dispersing. This collimation is a direct result of the strong magnetic fields and relativistic effects near the black hole. Observing these jets gives insight into how black holes can influence their surroundings over distances vastly larger than their own size. The speed of matter in TON 618's jets is near light speed. At these velocities, relativistic effects dominate. Time dilation, length contraction, and Doppler boosting all play a role in how the jets appear to distant observers. Doppler boosting, for instance, makes the jet pointed toward Earth appear brighter, while the counterjet pointed away appears dimmer. This effect explains why many quasars show highly asymmetric jet brightness. In the case of TUN 618, its jets likely carry energy that is difficult to measure directly because of these relativistic effects. But the overall luminosity of the system suggests that the jets are among the most powerful known in the universe. Jets from TUN 618 interact with the surrounding interstellar and intergalactic medium, carving out cavities in the gas and influencing star formation in neighboring regions. As the jets propagate, they transfer energy and momentum to the surrounding material. This process can trigger shocks, compress gas clouds, and even halt star formation by dispersing the gas. For a black hole of TUN 618 scale, these effects occur over hundreds of thousands of light-years, shaping not only its host galaxy, but also nearby cosmic structures. The feedback from these jets represents a crucial piece of the puzzle in understanding how hypermassive black holes influence early galaxy evolution. The jets themselves are composed of plasma, electrons, positrons, and possibly protons, all moving at relativistic speeds. Magnetic fields in the jets are twisted into helical structures, guiding the plasma along narrow channels. Turbulence, instabilities, and shocks develop along the jets, producing complex patterns of radiation. Observing the jets at different wavelengths reveals different layers of this structure. Radio observations map synchrotron emission from relativistic electrons spiraling along magnetic field lines, while X-rays reveal regions where particles are accelerated to extreme energies. For TUN 618, the immense luminosity ensures that the jets are detectable across cosmic distances, even though they originate from a black hole smaller than a solar system in size. Relativistic jets provide indirect measurements of the black hole's spin and accretion rate. The faster a black hole spins, the more energy it can extract from the rotational frame-dragging effect, a phenomenon predicted by general relativity. This rotational energy contributes to jet power. Observations of jet luminosity, combined with models of accretion physics, allow scientists to estimate how fast TUN 618 is spinning. Spin measurements are crucial because they inform theories of black hole growth and the efficiency of energy extraction. A hypermassive black hole like TUN 618, producing jets at near-light speed, likely has a spin close to the theoretical maximum, although precise measurement requires advanced instruments and multi-wavelength data. The size of the jets is staggering. While TUN 618 itself is smaller than the orbit of Saturn, the jets extend hundreds of thousands of light-years, dwarfing its host galaxy. This disproportion between the black hole and its influence illustrates the power of relativistic phenomena. The jets are highly collimated and maintain their structure despite interactions with interstellar clouds, turbulence, and gravitational effects from the galaxy. Observing the morphology of these jets provides clues about magnetic field alignment, plasma density, and the mechanics of energy transfer from the black hole to its environment. Jet formation also involves the extraction of energy from the accretion disk itself. Matter spiraling into TUN 618 releases gravitational energy, a portion of which is converted into electromagnetic energy and kinetic motion of particles. This process is highly efficient in hypermassive black holes. For smaller black holes, accretion converts a few percent of mass into energy, but in TUN 618, efficiencies may approach 10% or more. This extreme efficiency explains why the jets are so luminous and powerful, despite the vast distances they travel. The interaction between jets and radiation from the accretion disk produces additional complexity. Disk winds, which are outflows of ionized gas perpendicular to the disk, can interact with the jet, creating shocks and enhancing particle acceleration. These interactions produce variability in jet brightness, spectral lines, and polarization. TUN 618's jets likely experience these effects at an extreme level, given the enormous mass and energy scales involved. Observing these interactions in detail will provide insight into the coupling between accretion disks and relativistic outflows. Relativistic jets are also responsible for seeding cosmic magnetic fields. As the jets move through intergalactic space, they carry magnetic energy far from the black hole. These fields can influence the formation of other galaxies and the motion of gas in filaments of the cosmic web. TUN 618, with its hypermassive jets, represents a significant source of magnetization in the early universe, shaping the environment over scales of hundreds of thousands of light-years. Observing the jets of TUN 618 requires multi-wavelength astronomy. Radio telescopes like the Square Kilometre Array, SKA, can map the synchrotron emission, revealing the structure and orientation of the jets. X-ray observatories detect regions where particles reach extreme energies, while infrared and optical instruments trace gas and dust illuminated by the jets. Combining these observations allows scientists to build three-dimensional models of the jets, their velocity profiles, and the impact on surrounding gas. For TUN 618, such studies are challenging due to distance, but upcoming instruments promise unprecedented detail. Jets provide clues about black hole growth mechanisms. The energy carried away by the jets represents angular momentum extraction from the system. This means that as TUN 618's jets carry energy into space, they also influence the rate at which matter can spiral into the black hole. Understanding this balance helps explain how hypermassive black holes can accumulate mass so rapidly without self-limiting. TUN 618 offers a natural laboratory for studying these processes at scales far beyond those accessible in the local universe. Relativistic jets are prone to instabilities. Kelvin-Helmholtz instabilities, kink modes, and magnetic reconnection events produce turbulence along the jet. This turbulence affects particle acceleration, radiation emission, and the overall morphology. For TUN 618, the extreme energy density means that instabilities develop on scales far larger than in smaller black holes. Observing these phenomena informs models of jet stability, energy dissipation, and plasma physics under relativistic conditions. The orientation of TUN 618's jets relative to Earth affects observations. Jets pointed toward us appear brighter due to relativistic beaming, while those angled away appear dimmer. By modeling the observed luminosity and jet structure, scientists can infer the angle of the jets and estimate intrinsic power. This information is crucial for understanding the total energy budget of the black hole and the distribution of energy into the surrounding universe. Jets also influence the intergalactic medium. As the jets propagate, they heat and ionize gas over vast distances, contributing to cosmic reionization in the early universe. TUN 618, existing when the universe was only a fraction of its current age, may have played a role in this process, affecting the ionization state of hydrogen in its surroundings. Observing the effects of the jets on nearby gas clouds provides indirect measurements of their power and impact. The composition of the jets, whether primarily electrons and positrons or heavier ions, affects dynamics and radiation. Synchrotron emission and inverse Compton scattering depend on particle type and energy. Observations of TUN 618 across multiple wavelengths allow scientists to model particle populations and magnetic field strengths, revealing the physical conditions inside these extraordinary outflows. Jets are not uniform. They often contain internal shocks, knots, and regions of enhanced emission. These features indicate episodic variations in accretion rate, magnetic field alignment, or instabilities in the plasma. TUN 618's hypermassive scale amplifies these effects, producing structures that may span tens of thousands of light-years along the jet. Observing these knots provides insight into the dynamics of relativistic outflows and the connection between accretion events and energy release. Relativistic jets can also produce high-energy neutrinos and cosmic rays. Particles accelerated in shocks within the jet can escape the system and travel across intergalactic space. TUN 618, due to its immense energy output, may contribute to the flux of ultra-high energy particles in the universe, providing a natural source for multi-messenger astrophysics. Detection of these particles could link black hole activity to cosmic radiation observed on Earth. Magnetic reconnection events in jets release bursts of energy that accelerate particles and produce flares. For TON 618, the scale of these events is enormous, with energy releases potentially exceeding the output of entire galaxies over short timescales. Observing variability in jet emission across radio, optical, and X-ray wavelengths allows scientists to study these processes in action, revealing how energy is transferred from the black hole to its surroundings. Relativistic jets provide a natural laboratory for testing general relativity under extreme conditions. Matter moving at near-light speed in intense gravitational fields experiences time dilation, frame dragging, and other relativistic effects. By modeling jet motion, luminosity, and emission line profiles, scientists can infer the influence of the black hole's gravity on high-speed plasma, extending tests of physics to scales unattainable elsewhere. Jets from TON 618 serve as a probe of cosmic history. Their interactions with gas, dust, and radiation over billions of light-years carry information about the density, composition, and structure of the early universe. Observing how these jets propagate and interact with their environment allows scientists to reconstruct the conditions of the cosmos when TON 618 first formed, providing insight into the interplay between hypermassive black holes and the evolving universe. TON 618 is not only hypermassive, but also a master of energy transformation. Its relativistic jets are visible across billions of light-years because this black hole is extremely efficient at converting gravitational energy into motion and light. Understanding how energy is transferred from the black hole and its accretion disk to the particles that make up the jets is central to unlocking the mysteries of hypermassive quasars. Unlike smaller black holes, TON 618 operates at mass and energy scales that challenge conventional physics, and its jets offer one of the few windows into these extreme processes. The starting point of energy transfer lies deep within the gravitational well of the black hole. Matter falling toward TON 618 carries potential energy that increases dramatically as it approaches the event horizon. For hypermassive black holes, the difference in gravitational potential between the outer accretion disk and the innermost stable orbit is immense. As matter spirals inward, gravitational energy is converted into kinetic energy, causing particles to accelerate to speeds approaching light. This acceleration is not uniform. Turbulence in the disk, magnetic fields, and relativistic frame dragging create regions of intense shear and differential rotation. These regions act like natural particle accelerators, injecting energy into the plasma before it is launched in the jets. Magnetohydrodynamics, or MHD, governs much of the energy transfer. The plasma in the inner accretion disk is fully ionized and highly conductive, meaning it interacts strongly with magnetic fields. As the disk rotates, it twists and stretches these fields, creating helical structures that act as channels for energy. In TON 618, the mass and spin are so extreme that the magnetic fields are amplified to levels unseen in smaller black holes, providing the scaffolding for channeling gravitational energy into directed kinetic motion. This energy flows along the magnetic field lines, which constrain the plasma into narrow beams, preventing the outflow from dispersing prematurely. The magnetic fields themselves store enormous energy, which can be released in bursts when field lines reconnect, adding spikes of power to the jets. The extraction of rotational energy from the black hole itself is another key mechanism. The black hole's spin drags spacetime around it, an effect predicted by general relativity known as frame dragging. Charged particles in the plasma interact with this twisted spacetime and the associated magnetic fields, allowing some of the rotational energy to be tapped. This process, sometimes referred to as the Blandford-Znajek mechanism, channels spin energy into the jets, boosting particle velocities and energizing the emitted radiation. In Ton 618, the scale of spin and mass amplifies this process, producing jets that are extraordinarily powerful, able to maintain near light speeds across hundreds of thousands of light years. Energy conversion within the jets themselves is a complex process. As plasma moves along magnetic field lines, kinetic energy, magnetic energy, and thermal energy constantly exchange forms. Shock fronts develop when faster plasma catches up with slower moving material, converting kinetic energy into heat and accelerating particles further. Turbulence and instabilities, such as kink modes or Kelvin-Helmholtz instabilities, redistribute energy across the jet, allowing it to maintain collimation and propagate without dispersing. The combination of magnetic confinement, plasma pressure, and relativistic effects ensures that the energy injected near the black hole is efficiently carried across vast cosmic distances. Radiative processes also play a role in energy transfer. As electrons spiral along magnetic fields, they emit synchrotron radiation, releasing energy in radio, optical, and X-ray wavelengths. Inverse Compton scattering occurs when high-energy electrons collide with lower-energy photons, boosting the photons to gamma-ray energies. These processes allow a fraction of the kinetic and magnetic energy of the jet to be radiated, making Ton 618's jets visible across the electromagnetic spectrum. The efficiency of these radiative transfers depends on the density of particles, magnetic field strength, and photon field intensity. For Ton 618, the immense energy scales mean that synchrotron and inverse Compton processes are occurring at levels far beyond typical quasars, making the jets extraordinarily luminous. Energy transfer is not limited to the material in the jets themselves. The surrounding interstellar and intergalactic medium absorbs part of the jet's energy, producing shocks and heating gas clouds. This feedback injects energy into the environment, influencing galaxy formation and cosmic structure. As the jets plow through gas, kinetic energy is converted into thermal energy, ionizing hydrogen and accelerating secondary particles. The scale of Ton 618's jets ensures that this feedback occurs over hundreds of thousands of light years, transferring enormous amounts of energy into the surrounding cosmos. The structure of the accretion disk directly affects how energy is transferred to the jets. Inner regions near the innermost stable orbit are dominated by radiation pressure, while outer regions are dominated by gas pressure. The boundary layer between these regimes is where the most efficient energy extraction occurs. Plasma in this zone is exposed to intense gravitational shear and magnetic tension, resulting in magnetic reconnection events that release stored magnetic energy. These events can produce sudden increases in jet power, observed as flares or knots along the jet axis. In Ton 618, the scale of the disk means that these energy releases are orders of magnitude larger than in smaller systems. Another critical aspect is the role of accretion rate in energy transfer. Ton 618's hypermassive black hole consumes matter at an astonishing rate, yet the luminosity of its jets suggests that only a fraction of the available gravitational energy is converted into radiation. Much of the remaining energy is channeled into kinetic motion, carried along the jets. This division between radiative output and kinetic energy is essential to understanding how the black hole grows while producing relativistic jets. The interplay between feeding rate, disk viscosity, and magnetic field strength determines the fraction of gravitational energy converted into directed jet motion. The plasma composition affects energy transport as well. Electron-positron plasma behaves differently from electron-proton plasma, particularly in terms of mass loading and acceleration. Lighter particle populations achieve higher velocities more easily, allowing energy to propagate efficiently along the jet. In Ton 618, observations suggest that the jets may be dominated by electrons and positrons, maximizing the kinetic energy transmitted per particle and enabling near light-speed motion across vast distances. The density and composition of the plasma also influence radiative efficiency, determining how much energy is converted into observable emission. Magnetic reconnection is a repeated driver of energy redistribution. When twisted magnetic field lines snap and reconnect, stored magnetic energy is converted into particle kinetic energy and radiation. In TUN 618's jets, these events are amplified by the extreme mass and spin, producing localized bursts of energy that propagate along the jet. These bursts can create observable bright knots in the jet, evidence of episodic energy transfer events occurring thousands of light years from the black hole. Reconnection events also seed turbulence, which further redistributes energy and stabilizes the jet over cosmic distances. The conversion of gravitational potential into magnetic energy, and subsequently into kinetic energy, is a highly efficient chain in hypermassive black holes. Matter falling into TUN 618 releases gravitational energy that twists and stretches magnetic fields. These fields act like a spring, transferring energy into the plasma, which accelerates along the jet axis. The efficiency of this process depends on the alignment of the magnetic field with the black hole's spin axis and the rate at which the disk injects angular momentum into the fields. TUN 618 operates at a scale where this energy transfer reaches levels far beyond what is seen in smaller quasars, producing jets capable of reshaping surrounding intergalactic environments. Energy transfer is dynamic. As the accretion disk fluctuates, regions of higher or lower density create variations in the gravitational energy available for conversion. These fluctuations lead to episodic acceleration events, where pockets of plasma are launched at slightly different speeds, creating internal shocks along the jet. The interplay between magnetic confinement and plasma pressure allows these shocks to propagate without dispersing, ensuring that the energy reaches distant regions effectively. For TUN 618, the size and mass of the black hole mean that these internal shocks are more energetic and longer lasting than in smaller systems. The jets also transfer angular momentum from the black hole and disk into the surrounding medium. As the plasma moves outward, it carries not only energy, but also rotational momentum, gradually influencing the dynamics of nearby gas clouds and interstellar material. This mechanism helps regulate the growth of the black hole and the accretion disk, balancing the inflow of matter with the energy expelled in the jets. In TUN 618, the scale of this angular momentum transfer is immense, affecting structures far beyond the immediate host galaxy. Relativistic beaming concentrates energy along the jet axis, effectively transferring energy over vast distances without significant lateral loss. For TUN 618, the combination of near-light-speed plasma and tightly collimated magnetic fields ensures that the majority of the energy escapes along narrow beams. This beaming effect is critical for understanding the observed luminosity and for estimating the true energy budget of the jets, which would be underestimated if observed off-axis. The efficiency of this energy channeling is unprecedented, setting TUN 618 apart from smaller quasars. Energy transfer in TUN 618 is also influenced by the surrounding environment. Gas density, magnetic field interactions, and pressure gradients in the host galaxy affect how efficiently kinetic and electromagnetic energy propagate. Inhomogeneities in the medium can create shocks, turbulence, and magnetic reconnection events, all of which redistribute energy within the jet and into the environment. TUN 618's jets interact with the early universe medium, transferring energy into regions that are still forming stars and galaxies, imprinting its presence across hundreds of thousands of light years. Particle acceleration within the jets represents the final stage of energy transfer. Gravitational, magnetic, and kinetic energy are converted into high-energy motion of electrons, positrons, and possibly protons. These particles emit radiation across the electromagnetic spectrum, carrying energy away from the black hole in forms that can be observed across billions of light years. In TUN 618, the extreme scale of the black hole means that particles achieve energies far higher than in typical quasars, producing observable radiation from radio waves to X-rays and potentially gamma rays. The efficiency and scale of energy transfer in TON 618's jets are critical for understanding hypermassive black hole physics. The processes involve coordinated conversion of gravitational potential, disk dynamics, magnetic energy, and plasma motion into powerful, focused, relativistic outflows. Observing these mechanisms, both directly and indirectly, allows scientists to probe physics under extreme gravity, high energy density, and relativistic conditions that cannot be reproduced elsewhere in the universe. What upcoming telescopes might reveal. TON 618 sits at the farthest reaches of observation, 10.8 billion light-years away, glowing like a beacon from the early universe. Its light reaches Earth after traveling across most of cosmic history, carrying information about the black hole, its accretion disk, and possibly its host galaxy. Despite the incredible distances, advances in telescope technology promise to peel back layers of uncertainty, revealing details that have so far been invisible. Observing TON 618 with next-generation instruments will transform what scientists can know about extreme black holes, early galaxy formation, and the physical limits of mass and luminosity in the universe. The James Webb Space Telescope, JWST, has already provided a window into high redshift quasars, but TON 618 stretches the limits of resolution and sensitivity. JWST operates in infrared wavelengths, which are crucial for observing distant objects whose light has been redshifted by the expansion of the universe. Infrared spectroscopy allows astronomers to detect the signature of elements in the quasars surrounding gas, measure velocities of material in the accretion disk, and estimate the mass of the black hole with greater precision. For TON 618, JWST could identify features in the disk spectrum that are invisible at optical wavelengths, such as thermal emission from hot dust or specific ionized elements. Observing the continuum of emission across multiple infrared bands can map the temperature profile of the disk, providing clues about how matter spirals inward at extreme mass scales. JWST's sensitivity also allows for the search for a host galaxy. TON 618's quasar is so luminous that it outshines its galaxy, making direct observation extremely difficult. Infrared imaging at high resolution could isolate faint stellar light around the quasar, offering estimates of the galaxy's mass, structure, and star formation activity. Detecting a faint bulge or disk would help clarify whether TON 618 grew independently of its galaxy or if the galaxy simply remains below current detection limits. JWST could also identify surrounding satellite galaxies or dense gas clouds, providing insight into the black hole's early environment and potential sources of accretion. The Extremely Large Telescope, ELT, promises even higher spatial resolution in the optical and near-infrared. Its 39-meter primary mirror will gather vastly more light than current ground-based telescopes, allowing for detailed studies of faint features near TON 618. ELT's adaptive optics system can correct for atmospheric distortions, producing images with sharpness approaching space-based telescopes. For TON 618, this could mean resolving fine structure in the accretion disk's outer regions, detecting gas flows around the black hole, or even mapping the distribution of nearby stars and gas within the host galaxy. Spectroscopic instruments on the ELT could separate overlapping emission lines, giving precise measurements of gas velocities and chemical composition, essential for understanding accretion physics and feedback processes. ELT's ability to conduct time-resolved observations opens the possibility of monitoring variability in TON 618's light output. Accretion disks around hypermassive black holes can fluctuate over days, months, or years, producing changes in luminosity and emission line widths. Measuring these variations provides a dynamic view of matter moving near the event horizon, turbulence within the disk, and instabilities in accretion flows. For a black hole as massive as TON 618, Even small changes in the disk's structure or feeding rate can produce observable effects at Earth when analyzed with high-precision instruments. The Square Kilometre Array, SKA, will revolutionize observations of radio emissions from quasars. TUN 618 emits powerful relativistic jets that produce radio waves across vast distances. SK's unprecedented sensitivity and resolution can map the structure of these jets, revealing their orientation, energy distribution, and interaction with surrounding intergalactic gas. Observing jet morphology can test models of magnetic field configuration, energy extraction from the black hole's spin, and relativistic effects near the event horizon. For a hypermassive black hole, jets could extend hundreds of thousands of light-years, affecting the formation of neighboring galaxies and the flow of gas within the cosmic web. SKA also offers the possibility of detecting faint radio emission from the host galaxy. Even if stellar light remains invisible due to the quasar's luminosity, synchrotron emission from supernovae or star-forming regions could reveal the galaxy's presence. This data would help determine whether TUN 618 resides in a dense galactic environment or a more isolated region, providing clues about the interaction between black holes and galaxy formation at high redshift. Next-generation X-ray observatories will probe the most energetic regions near the black hole. TUN 618's accretion disk emits extreme X-rays from its innermost regions, where temperatures reach millions of degrees, and gravitational forces approach the limits of general relativity. X-ray spectroscopy can measure ionized ion lines, revealing the velocity of matter orbiting near the event horizon. Broadening and skewing of these lines provide direct evidence of relativistic effects, including time dilation and gravitational redshift. For TUN 618, X-ray measurements could estimate the spin of the black hole, a fundamental parameter that influences accretion efficiency and jet production. High-energy observations also allow scientists to study the corona above the accretion disk. The corona is a region of highly energized particles emitting X-rays, and its structure remains poorly understood. Observing how the corona interacts with the disk and produces variable X-ray emission offers insight into energy transport mechanisms and magnetic field behavior. TUN 618's extreme mass and luminosity make its corona an ideal laboratory for testing models that cannot be examined in less massive systems. Combining multi-wavelength data from JWST, ELT, SKA, and X-ray observatories allows for a complete picture of TUN 618. Each wavelength reveals a different layer of the system: infrared traces, cooler dust, and stellar components. Optical maps ionized gas in the disk, radio captures jets and synchrotron emission, and X-rays probe the innermost energetic regions. By cross-referencing these observations, scientists can constrain models of accretion, jet formation, and host galaxy properties. Multi-wavelength studies also reduce uncertainties caused by distance, redshift, and quasar luminosity, providing a more accurate understanding of this hypermassive black hole. Upcoming telescopes also enable studies of chemical composition in the early universe. TUN 618's accretion disk and surrounding gas contain information about the first generations of stars and supernovae. Spectral lines reveal the abundance of elements like carbon, oxygen, nitrogen, and iron, providing a record of nuclear synthesis during the universe's first billion years. High-resolution spectroscopy from ELT and JWST could detect subtle variations in elemental ratios, indicating processes of early chemical enrichment and feedback from massive stars. Understanding these ratios informs models of star formation, galaxy evolution, and the role of hypermassive black holes in distributing energy and elements. Time domain studies will become increasingly important. Monitoring TUN 618 over months or years can reveal periodic variations or flares caused by instabilities in the accretion disk or interactions with orbiting material. Observing these changes in multiple wavelengths can identify causal links between disk physics, jet activity, and energy output. For a black hole of this scale, even slow variability can indicate massive inflows or changes in the feeding rate. providing a dynamic understanding of how matter behaves near a hypermassive event horizon. Next-generation instruments also promise advances in gravitational lensing studies. TON 618's light passes through intervening galaxies and matter along the line of sight, producing distortions that can be analyzed to study dark matter distribution and cosmic structure. JWST and ELT can detect subtle lensing effects, offering a way to map the mass and distribution of matter between Earth and TON 618. Such studies connect the black hole to the larger-scale structure of the universe and inform cosmological models of matter distribution at high redshift. The combination of high sensitivity and high resolution will allow for direct measurements of accretion rates. By comparing luminosity and spectral features, scientists can estimate how much matter is falling onto TON 618, how efficiently it converts mass into radiation, and how this process scales with black hole mass. These measurements test theories that currently struggle to explain how hypermassive black holes grow so quickly in the early universe. TON 618 provides a natural laboratory for observing processes at mass scales that cannot be replicated nearby. Upcoming telescopes may also reveal the presence of companion structures, such as star clusters or smaller black holes in orbit around TON 618. These companions can influence accretion dynamics, contribute to mergers, and affect jet orientation. Observing these interactions offers insight into hierarchical growth processes and the role of environment in black hole evolution. Detecting gravitational interactions with nearby matter provides a dynamic view of how TON 618 interacts with its surroundings on both galactic and intergalactic scales. Polarimetric studies will add another dimension. Light emitted from the accretion disk and jets can be polarized, providing information about magnetic field orientation, scattering processes, and disk geometry. Instruments on ELT and future X-ray observatories can measure polarization at high resolution, revealing the structure of magnetic fields in extreme environments. For a hypermassive black hole, these measurements test the limits of theoretical models, providing constraints on disk and jet physics in conditions far beyond anything observable in smaller systems. Next-generation facilities may also probe the innermost stable circular orbit, the closest region where matter can orbit before plunging into the black hole. For a black hole as massive as TON 618, this radius is enormous in absolute terms, yet relativistic effects are extreme. X-ray spectroscopy combined with high-resolution infrared imaging could provide indirect measurements of disk truncation, orbital velocities, and energy release mechanisms. These observations refine understanding of how matter behaves near hypermassive event horizons, offering a glimpse of physics in the strongest gravitational fields. Observing TON 618 across multiple instruments will also refine the measurement of its spin. Black hole spin influences accretion efficiency, jet production, and relativistic effects in the innermost disk. By measuring the broadening of spectral lines, relativistic Doppler shifts, and the orientation of jets, astronomers can infer the spin parameter. Spin information reveals clues about the black hole's formation history, whether it grew primarily through mergers or prolonged accretion, and how angular momentum is distributed in hypermassive systems. TON 618 provides a testbed for high-energy particle acceleration. Jets and the inner accretion disk accelerate particles to relativistic speeds, producing X-rays, gamma rays, and potentially cosmic rays. Observations from next-generation X-ray and gamma-ray observatories will constrain models of particle acceleration, magnetic reconnection, and energy dissipation in extreme gravity. These processes cannot be observed directly in smaller systems, making TON 618 a critical laboratory for high-energy physics. Upcoming telescopes will also allow better measurement of redshift and distance. TON 618's light has traveled 10.8 billion years. But precise redshift measurements refine estimates of cosmic expansion, time of formation, and environmental conditions. High-resolution spectroscopy across multiple wavelengths reduces uncertainties, providing a more accurate picture of the black hole's epoch and the surrounding universe's density, temperature, and ionization state. TUN 618 will help map the cosmic web at high redshift. Its radiation interacts with intervening gas and galaxies, producing absorption features that trace matter distribution. Next-generation instruments will detect finer structures in these absorption lines, revealing filaments, voids, and overdensities in the early universe. These observations connect the black hole to large-scale structure formation, providing insight into how matter organized itself during the first few billion years after the Big Bang. Multi-wavelength campaigns will also clarify feedback mechanisms. Jets, radiation pressure, and outflows from TUN 618 influence surrounding gas. Observing these effects in infrared, optical, radio, and X-ray bands allows scientists to model how hypermassive black holes regulate star formation, redistribute energy, and shape early galaxies. Feedback processes are essential for understanding why TUN 618 could grow so massive without dispersing its feeding material too quickly. Spectropolarimetry can reveal more about the alignment of the accretion disk, magnetic fields, and jet axis. Measuring the angle and degree of polarization at different wavelengths tests models of relativistic disk physics and jet launching mechanisms. TUN 618, due to its extreme luminosity, produces signals strong enough for detailed polarimetric studies, despite its distance, allowing unprecedented access to the geometry of a hypermassive quasar. The next generation of telescopes will also provide time-resolved monitoring across the electromagnetic spectrum. Variability in TUN 618's light can reveal instabilities in accretion, episodic feeding events, and interactions with orbiting matter. High-cadence observations allow scientists to connect physical changes in the disk to observed luminosity changes, giving a dynamic view of matter falling into one of the universe's largest black holes. Observations will also constrain the chemical evolution of the early universe. TUN 618's emission lines carry information about metallicity, ionization states, and elemental ratios in the surrounding gas. High-resolution spectroscopy will measure abundances with unprecedented precision, revealing how early star formation, supernovae, and chemical enrichment occurred in the environment of a hypermassive black hole. Finally, combining data from all these instruments, JWST, ELT, SKA, X-ray observatories, will allow scientists to model the full energy budget of TUN 618. Its accretion disk, jets, corona, and radiation output can be integrated into a comprehensive picture, revealing how matter, energy, and light interact in a hypermassive quasar. This will inform theories about the limits of black hole growth, early galaxy formation, and the behavior of matter under the strongest gravity in the universe.